I'm blue, dabba dee dabba die, dabba dee dabba die, dabba. Is that scary? Still scary? Scary every time? Or did that just sound like someone was playing music outside on the street or something? I try what I can, to to not make people panic immediately. Let's do the. It will never stop being scary. Damn it. What if I just kicked it off straight with like Crazy Frog or something? Yeah, there's always someone who forgets that they'd opened this tab somewhere and they're doing something else over somewhere else. um, I assume this means that audio is working and you can all hear me fine. Blue for the win. Excellent. All right. Let's see. Audio's found, loud and clear, ready for ASMR. Great. That's what I want to hear. First time catching the stream live. That's exciting. Welcome. Let's see over here. Okay, let's see if we can get video working too. Now you should see my face. I'm trying new glasses today, so it'll be a different look than what you might be used for. I still have my old ones, but I'm trying out this look and seeing how I feel about it. You can see them in all their glory now in the full view. Oh, congrats! That's exciting. I take it you can all see me. Cool glasses, nice. Handsome as hell, I'll take it. All right, so that means you can see me, you can hear me. The glasses scared me more. Does the audio look like it's synchronized to me talking? This is a check that's useful to do every time. It's very hard to tell, especially if you're wearing like Bluetooth headphones, because then usually they introduce an audio delay too. But I'm guessing that this should be aligned already. Audio is perfect, loud and clear. Okay, fantastic. That makes me happy, and I think we're right on time. If it's a tad quiet, I recommend turning up your sound. I think it's supposed to be like looking at the meter on my output. It's supposed to be exactly right. Okay. Now let's see if I do this. If you can see my screen, you should see welcome to Jay's Herd, the Discord server. I get a lot of requests for Rayon on a stream. I might do a decrusted on them at some point. You can see a Discord. Okay, fantastic. Then I think we are just about ready to start. Oh, yeah, if you wanna see, yeah, I know, white Discord. I know. It makes you all very sad and very upset. All right, let's see. If you want to compare it to the old ones. Old? New. Old? New. Oh, I guess now you only see it small. Oh, well. Too bad. Next stream, do a bigger compare. Okay. Let me then, before we start, make this also dark so that you don't all come yelling at me. I don't remember if they have a native... Oh, they do have a native dark theme now. Okay, great. Here, see? You can all stop yelling at me now. MattClad's page, I don't think has a dark mode, but I can do the good old... what is the... it's like here, and then filter... Invert. No, filter... Boom. Now it's dark. How do you like that? And this one's not going to stay up very long, so this one will be fine. Okay, how about we get started now that it's all set up. So let me just hit the record, and then we'll Let's see. Hi folks, welcome back to yet another stream, another Impl Rust stream. This one is going to be in line with some of the previous streams we've done where we implement sort of following a little bit of a programming challenge, if you will, or we sort of code along with a sequence of challenges. In this particular case, we're going to be following the Codecrafters Build Your Own Interpreter. And the reason for this is because, well, I've really wanted to do a stream on especially parsing, but also on writing an interpreter. And so now that there is one where there's sort of a well-defined path to walk through, that feels like a good opportunity to do so. What I'll also add is that I've gotten a lot of really good feedback on the videos where we walk through, especially these sort of well-defined challenges that other people can work through on their own time, because some people like to just sort of have this video running at the same time and try to solve it with me, like sort of pair programming. Some people like to, after the recording of this stream is up, basically try to do it themselves, and after they finish each part, go and sort of compare to how I did it, and then do that over and over again, which is harder to do for just implementing something completely random that you don't really have a guide to implementing yourself. And so we're going to kick that off in a second. If you are in chat, then what I will send in chat now is a link you can use to join so that you can, I think you get like a week free or something. This particular challenge is also in beta, which is hard to read here. It's in beta, so it is freely available. It's also actually available on GitHub. If you're watching this after the fact, I'll put the link in the video description. Let me see if I can dig up the free one interpreter. It is this one. I'll send that in chat right here. Codecrafters, all of the challenges are also on GitHub. That comes without all the like testing infrastructure and stuff, but at least all the challenge text and sort of code snippet and stuff are there. So if you're not willing, sort of, if you want to go beyond the sort of 7 days here and you are not willing to pay for it, just use that one instead. It's not going to be quite as nice to work with, but it is at least a way that you can continue to work through it. I'll also add the same sort of stipulation that I've done before when I do the Codecrafter videos, that I'm not sponsored by Codecrafters. I do get a referral if you sign up through the link that is in the video description or in the chat when you do like the 7 days free. But apart from that, if I don't like things, I will call them out because I'm not being paid to make this video. Excellent. Okay. Before we kick off with we'll dive into it almost straight away, I just want to mention first, and this is going to be bright for the people who don't like bright screens. There is a Discord for my streams. You can get the invite link just by going to discord.johnwho.eu, and it'll redirect you to the Discord invite link. And that has information about like the various things that I make, as well as information about sponsorship, if that's something you're interested in doing, as well as an announcements channel that you can subscribe to. And that's where I announce whenever I will do upcoming streams and the like. I'm also on the various social media, but if you prefer to get it through Discord, then you can go in there and do that. Okay. Then I think we are ready. The Discord link is just discord.johnwho.eu. I'll put it in the link here as well. Okay, let's dig right into it. The Building Your Own Interpreter challenge, there were two reasons really why I really want to do something like this. The first one is there's an article by Mattclad it's from 2020, so it's not a super recent article, but where Mattclad writes about Pratt parsing, which is a particular way to write parsers that is actually fairly straightforward, but also quite powerful. It is, I think, is a really fun article to read if you're not very experienced with parsers, or even if you are and you just want like, here's a sort of cookie cutter good way to just do simple parsing that allows you to deal with things like associativity and the like. We'll probably follow something like this article in the implementation. So if you haven't read it, I recommend either you pause and go read it, or you'll sort of follow through as I do it, and you can read the whole article later. The other reason why I wanted to do this one is I like the fact that it's based on a book. The Crafting Interpreters book, which has a website. I'm not going to open it because it's a very bright page and people apparently don't like that. But I believe at least parts of the book are available freely online as well, or of course buy the book and support the author. But I like the fact that it sort of follows a well-developed resource. So with that, I think we're just going to start. Now, the interesting thing about building an interpreter for any language is that there is an underlying language that you are supposed to interpret, right? Like Python is an interpreted language too, but the Python language is not trivial. I think the idea here with LOX, which is the language that is sort of used in this Crafting Interpreters book and that we're going to be working with here, is that it's a fairly simple language. I have not looked at it, so I do not know. But given it's intended for writing your interpreter, I'm guessing that it's at least not a super complicated language to at least parse and work with. You can probably, it might even be Turing complete, who knows? So you can probably build interesting things with it, but that's where we'll start. Before starting this challenge, make sure you've read the welcome part of the book that contains these chapters. I have not read any of those chapters, so we will skim through them quickly. Let's see if there's a dark mode for this. I don't think there is, so we're going to do our little trick here and say filter invert for that. And we'll do the same thing here. Inspect HTML, filter invert. And we'll do the same for this guy. This and element filter invert. I know there are extensions for this, but I don't actually care about dark mode myself, so I don't have them. All right. Introduction. I'm going to skim through this pretty quickly. Okay, this is a welcome. Great. Why learn this stuff? I know lots of reasons to learn this stuff. The languages are everywhere. That is true. There are a lot of like special purpose-built languages, and sometimes it's really cool to be able to write your own for whatever little DSL that you want, domain-specific language you want. Languages are a great exercise, so I agree with that too. Close to the author's heart, that's nice. Book is organized with code snippets, asides, challenges, design notes. The first interpreter. We'll write our first interpreter, JLOX, in Java. Well, we're not going to do that. We're going to write it in Rust, of course. I almost said C. We're not going to write it in C. Okay. Don't care too much about that. Oh, in the book, they implemented in C as the second language around. That's cool. Well, we're going to be the third language. We're going to do it in Rust. Map of the territory. Parts of a language. Okay, so this is worth talking a little bit about. I know some of this from before, so rather than sort of reading this verbatim, which you can do on your own time, I'm just going to talk roughly about like the parts that exist in a language. And I'm not a specialist at this either, so I'm sure I'll get some things right, but at least enough that we can work our way through this. The way we'll think about this is that when you have any programming language, the thing you start with is source code. It's like it's a text file. And ultimately what you need to turn that into is, as you see all the way on the right on the mountain here, machine code. So you start from source code and you need to get to machine code. The journey you can take to get there is there are actually a lot of different ways to get there. But all of them start in the same way. The first of them is you need to scan the text and turn it into tokens. So this is often called tokenization or lexing. And what this is taking the individual like ASCII or UTF-8 characters and recognizing words like struct or enum or fn or curly brackets as being, special in some sense. That group of characters that make up like struct are actually one logical unit. It is one token. And so you're turning the individual string of characters into these well-defined tokens. After you have the tokens, you then have to do parsing. So parsing is when you go from this sequence of tokens. And in fact, if you look at Rust, in the Rust standard library, there's this thing called a token stream. And a token stream is a sequence of tokens. Or in the Rust case, it's a sequence of token trees. So they actually have done a little bit of parsing here. It's not fully unparsed. But the idea of a token stream in Rust is that this is what a procedural macro is given. So it's tokenized, it's lexed, and it's a little bit parsed. Like they parse out things like parentheses, for example, like groups, but that's almost the extent to which. And then you'll see that the main thing you have on a token stream is that it implements into iterator. It implements into iterator where every item in that iterator is a token tree, where that token tree is either a literal, a punctuation, an ident, so this is just a keyword, or a group, where a group is a delimited token stream, like parentheses, square brackets, or curly brackets. And so it's a very, like, it is strictly speaking a little bit more than just tokenization, because they do things like recognize groups, but it's essentially just tokenization. And then a procedural macro takes this and outputs a sequence of tokens that should be used to parse instead of the original stream. That's really all procedural macros are. They are a program from one tokenization that is the representation of what's in the source code to a replacement tokenization that should be the input to parsing. And so then after you give the sequence of tokens to the parser's job is to turn that into a syntax tree, often known as an abstract syntax tree. A syntax tree is a representation of the sort of logic that underpins the sequence of tokens that you have, so how they are related. This is where you might do things like recognize that async fn is actually one function, like they are logically grouped together as an async fn being a sort of unit. If you wanted to see something like this in Rust, you could look at something like the syncrate. So if you look at the syncrate, it provides parsing. So not just tokenization, but actually parsing. And if we look down at the types that you have here you have things like field, expressions, generics, FN items, impl items, like it sort of knows about the logical constructs of the language. And in fact, if we look up the Rust reference, which I really should have already opened. So the Rust reference, here you see it talks about the tokens of Rust, right? So this is things like characters, strings, raw strings, bytes, etc. These are the things that you would tokenize or lex. And then items are the things that you would actually parse. So these say things like, this is the syntax for a function, right? It has things like self parameters, and it defines what all of these things are, how the tokens go together to form the constructs of the language. And so the output of the parser, or the sort of input to the parser, is the token stream and this definition of what the language looks like, the grammar of the language, which is what it's called. And the output of the parser is an abstract syntax tree, which is essentially it is a tree, as the name implies, that shows you the sort of hierarchy, such as, for example, if you parse a file, there'll be a sort of a node for this file, and then the children of that node will be all the top level declarations in that file. Say one of them is a module definition, then you'll have a module node, and that module node in the tree will have a bunch of child nodes, and each of those are the items within that module, such as an impl block or a type definition or whatever it might be. And so that's how you end up with this notion of an abstract syntax tree, is that is a tree representation of the items that have been parsed out of that file. Okay, so that's the idea of a syntax tree. And then the question becomes, how do you take a syntax tree and turn it into something the computer can execute? Well, there are a couple of ways to do that. One of them is to not actually produce machine code, but instead take that abstract syntax tree and hand it to another program that knows how to execute that. And this is how interpreted languages usually work, is that the output of the syntax tree is really just like it doesn't compute anything. The syntax tree is just a representation of all of the stuff, all the declarations in the file, but nothing has been executed. And then you hand that to a program, in Python's case, the Python binary, and it knows how to walk that tree and evaluate the items of that tree, so that, like, if it sees a for loop, it will actually execute a for loop sort of on your behalf. So your program is never directly turned into machine code. Another program is sort of using your input, your source code as instructions for what it should execute. And it has all of the machine code. Syntax tree it's not really a binary it's an abstract tree. It's never actually written to disk anywhere. It's sort of an in-memory representation of the semantics of whatever source file has been parsed. And so a high-level language like Python or Node.js will generally execute an AST. It will traverse the AST and then interpret it, execute it. The other thing you could do is you could turn it directly into machine code. This is what happens in a language like Rust or C, where you take the AST, you walk the AST using something that knows how to translate different concepts, like abstract concepts, into machine code, into assembly code. This is something that, LLVM is a good example of this. So LLVM takes as input a sort of abstract definition of operations like for loops or functions or function calls, and then knows how to sort of optimize those and turn them into executable machine code. And that's what you see this path here from syntax tree that goes up here through analysis and to intermediate representations. So LLVM has a bunch of these intermediate representations, and Rust, in fact, has its own called Mir, which is the middle intermediate representation. They also have HIR, which is the high-level intermediate representation. And so the sort of abstract syntax tree gets turned into HIR, which gets turned into MIR, which gets turned into LLVM IR, IR meaning intermediate representation here. And then the LLVM internally does a bunch of optimizations, sort of transformations over that graph to do things like move expressions out of loops if they don't depend on the variables within the loop, like optimizations passes like that happen not at the machine code level, but happen at the sort of more abstract semantic level. And then ultimately, what you end up with is some intermediate representation that is now ready to be transpiled or translated, if you will, almost directly into code generation. So by the time you get close to getting ready to do this code generation, the thing that actually generates machine code, at that point, your intermediate representation is usually quite close to assembly in the first place. It might no longer have a notion of loops, for example. Like, there isn't really a looping construct in machine code. In assembly, all you have is like a goto, you have a jump. And so a loop is you run a bunch of code, and at the end, you evaluate some condition, which is the loop condition. And if the condition is true, then you jump to the first instruction of the loop again. So there's no loop construct in assembly. And so this is an example of something where in the lowest intermediate representation, you might already have eliminated all loops and replaced them with gotos, because that's what you're going to need for the code generation step, which is that last bit that takes you into actually executable machine code. And then there's a variant of this, which is something like Java, where the thing that the compiler generates is not actually machine code. It's not assembly code that runs like on your CPU. It is actually sort of it is more like the high-level language approach. But what you hand it is not the abstract syntax tree for it to traverse and interpret like Python, but rather a sort of general purpose machine code. It's sort of a meta machine code that can then be interpreted by the Java virtual machine. That can then, sort of similar to Python, it has all the machine code, and it reads your the output of your intermediate representation, your bytecode, and evaluates that to basically execute your program on your behalf. So those are the sort of different paths here. And in our case, when what we want is an interpreter, generally what we mean is something that goes from source code, scans it into tokens, parses it into a syntax tree, and then interprets it by executing directly that syntax tree. So we're not, like in what we're doing here, I don't think we're going to do any of the sort of analysis or optimization of intermediate representations or generating any assembly code. I'm going to pause there because that was a lot to take in, and do sort of questions if you have them, and then we'll move on from there. Is the AST tree like objects? You can sort of think of it like that. Like it's a tree structure where all the nodes describe a particular item in the source tree, like a module or a function definition. Does the LLVM take IR as its input instead of an abstract syntax tree? So LLVM's input is actually also an intermediate representation. So in the Rust compiler, what actually happens is you take you parse into the syntax tree. You turn that into the high-level IR, like HIR. You turn that into mir, and then there's a bunch of optimization passes on that intermediate representation. And then eventually they move it to LLVM's IR, and at that point they call LLVM, and then LLVM does the remaining bits from there. Not sure, but I think Python also has a bytecode. I think you're right. So I think Python now has sort of a bytecode equivalent where you can sort of pre-compile your Python code into, like rather than just giving the raw source code file to Python, you can sort of pre-compile it, which is essentially turning it into bytecode, which is really just a byte representation of the syntax tree, if I remember correctly, so that you can then hand that to Python later, and it doesn't have to do the scanning and the parsing. It can just directly execute the resulting file. Will that include a GC? My guess is the language here is not complicated enough that it needs a GC, but we'll see. Okay. Since Golang is converted into binary but has garbage collector, how does that work? So a language like Go produces machine code, but the way to think about it is that there's a bunch of source code that is compiled into your binary, into your machine code that you have not written. So Go sort of comes with a bundled piece of source code that does the garbage collection, does a bunch of transformations on your source code so that it interacts with the runtime that they ship. But the runtime is sort of embedded in your binary. Whereas in Java, the runtime is a separate executable, the Java VM, that you hand your compiled Java file to, or compiled Java project rather. Bytecode is compiled assembly. Not quite. So bytecode is a sort of equivalent to assembly, but assembly is, or machine code rather, we should be technically accurate here. Arguably assembly is really just a programming language. But machine code is usually specific to a particular CPU. It might even, like it's to not just a particular family of CPU, it can even be specialized to a very specific architecture, a very specific instance of a CPU. Whereas bytecode is a sort of very low level language that can be run on many different CPUs. Locks does have a GC. It also has closures and inheritance. Ooh, this will be interesting to see how far we get through that. I'm excited to see. The Java chapter uses Java's GC. In Rust, I've used reference counting. Oh, so that's interesting. So if locks does have garbage collection, that means that we will have to act as the garbage collector for the language. We might just do that in a sort of simple way with reference counting or something. We'll see that when we get there. How much performance do you leave on the table by doing work in an interpreter compared to compiling it to machine code? It varies, but usually interpreted languages are slower than fully compiled languages because they have to do more work, right? Because they essentially have to do part of the compilation at runtime. Locks is more complete than you might think. It's like Lua. Well, then I'm excited to start implementing it. Go produces something called SSA. This is a single assignment. What's it called? I forget what the first S for. I think it's serial single assignment or something, which is a machine code that is not tailored to a particular CPU. And it's a very useful representation for being able to just execute a program after the fact. Static single assignment. That's what it is. Okay. So now that we have this sort of, we've explored this map of the parts of a language. We've talked about scanning. We talked about parsing. We'll get into this a little bit once we start writing the code. I don't want to do too much of this in advance. Static analysis is this idea of after you've parsed, you can then do a bunch of analysis, things like type checking, right? Where you check that if you try to call a function, then the function you're trying to call actually has the types that you gave for the arguments, for instance. So this is where you add semantic richness. So you no longer have just a function call, you actually have a specific function with a type signature. And so now you infuse your code with meaning, right? Like if you do a plus b, what does that mean? Intermediate representations, optimizations, code generation. We've talked about most of this now. I'm obviously skipping past a bunch of detail. Highly recommend you read this if you really want to get into the depths here, but I'm more trying to give us enough of the context that we need for starting to write some code. Single pass compilers. Yeah, so single pass compilers are a version of a compiler where rather than parse everything like into memory and then doing all these intermediate representations, they try to be a lot faster at compiling by not doing any of that. It tries to make sure that you can, as you parse almost, you produce the machine code. So you do a single pass through the file, and at the end, you've produced all the machine code. That does mean that you can end up with a way faster compiler. The downside is you can be a lot less smart about things like transformations because you haven't seen the later code yet, so you can't optimize based on it. But also because it forces declarations to happen in a particular way. So this is one of the reasons actually why, at least if I remember correctly, why in C, in older versions of C, you had to declare the signature of a function before you're allowed to call that function. So you don't have to give the body of a function at the beginning of the file. But like if you have two functions, foo and bar, and foo wants to call bar, you can't have foo first and then bar. That will not work. You have to have either you have to put bar before foo, or you have to put a declaration of the signature of bar first, and then you write foo, and then foo is allowed to reference bar, and then you put the definition of bar. Because it's this sort of single pass compiler. C has since evolved from that where you don't need to do that anymore. Tree walk interpreters are, as we talked about, things that specifically will take the AST and then execute the AST directly. And then transpilers are things that just take one representation of language and turn it into another one. So this is something like if you compile Rust to JavaScript, like WebAssembly is an example of a transpiler, because you're not producing machine code, you're producing just a different source code language that then gets executed in some other way. And then just-in-time compilation is what Python often does, for example, where you take the... it's basically you take the syntax tree, the abstract syntax tree, and when you need to call it, you compile that thing, and then you execute the machine code, right? And then the next time it gets called, you already produce the machine code, so then you can just call it again. So hence the name just in time. You compile it just when you need it, which can make the compiler phase really fast because it doesn't really need to compile anything. And instead you pay the cost of compilation only on first call. Oh, Python doesn't do JIT? No, Python does do JIT, I'm pretty sure. And JavaScript does JIT as well. Yeah, and this is one of those, like, it's a little bit weird to differentiate between compilers and interpreters, because interpreters sometimes do some compilation, like just-in-time compilation, and compilers do kind of interpret things like if you have a constant expression in C or a constant Rust that has an expression and not just a value, you actually have to execute code at compile time, which is really kind of an interpreter. So like these are not perfectly separate circles. They're actually fairly related. Oh, interesting. Yeah, so I guess, at least according to this, there are very few languages that are pure interpreters anymore. Well, I guess JLox apparently is. And then purely compiled languages, and then you have a bunch here that do things like JITs, where it's an interpreter, but it also does compile. Okay. So now to that chapter. And now the LOX language. And this obviously is an important thing for us to know, given this is the language that we're supposed to parse and interpret. Now, I don't think what we're going to do is try to fully understand the entire grammar and semantics of the language up front. That's going to be very hard. Instead, what we're going to do, and I'm guessing this is what this chapter will do as well, is give us an overview of the language. Like, what roughly does it look like? What's roughly the syntax? What kind of items does it have? How do you declare variables and the like? Yeah, exactly. I don't want to drag you through the reams of language lawyering and specifications before you get to touch your text editor. So it's a gently friendly introduction to LOX. Okay. Let's see. Okay, so comments are dash dash. Let me see if I can zoom in a little bit here. Yeah, now we're talking. Okay, so we have slash dash comments. We have print. We don't have parentheses around function arguments, which is interesting. Yeah, so LOX is pretty compact. It's kind of like JavaScript scheme in Lua. Looks the most like JavaScript. LOX is dynamically typed. Okay, so variables can store values of any type. You don't need to declare that this variable holds like a hash map, for example. It just holds what it holds, and it can change over time. Errors happen at runtime on types. That seems fine. Automatic memory management, that seems pretty reasonable too. You don't really want to have to write a bunch of freeze in your code. You want that to just be handled by the interpreter. And I think in our case, what we will almost certainly do is we'll do reference counting for keeping track of when variables should be deallocated and stuff, rather than a good garbage collector. We are going to write our own garbage collector. That's cool. I mean, we might end up doing that as well. I'm guessing that we're not going to get all the way to writing our own garbage collector in this video at least, but this might be a sort of beefy enough challenge that we end up doing a two-parter, and then part 2 might easily be the garbage collector. Data types. Okay, we have Booleans. That makes a lot of sense. We have numbers. There's only one kind of number, double precision floating point. Okay, so integers are floating points. Great. Strings and double quotes. And parsing strings is actually surprisingly difficult. Not strings like this, but once you have to be able to like escape characters, like what if you want to put a double quote inside of a string? What do you do then? Well, okay, let's say you do backslash double quote. Well, what if you want to put an actual backslash in the string? Well, now you need to support backslash. And so it gets interesting pretty quickly. And nil. Interesting. Does it not have, so it doesn't have arrays or maps. It just has Booleans, numbers, strings, and nil. Interesting. Expressions, it has arithmetic, plus, minus, multiply, and divide. So all 4 of these are infix operators. So infix operators are operators that sit in between their 2 operands. And then they also have a prefix operator for negative numbers. That makes sense. And plus also works on strings. Okay. A comparison and equality. We can compare numbers and only numbers with the standard comparison operators, equality, inequality, inequality for different types, which presumably always returns false. Logical operators. Okay, so this is the not operator, which is a prefix operator. So it's not an infix. It doesn't have 2 operands, one on each side. It is a prefix operator, so it's an operator followed by its operand. and then and, which is an infix operator for logical and, or infix for or. Okay. Precedence and grouping. Great. So this is the notion of you want to be able to put parentheses if, for example, you have A plus B times C, then normally multiplication binds tighter. So you would end up computing B times C and then adding A. But parentheses are the way that you would say, no, I really want A plus B and then multiply that with C. So you need something like parentheses to be able to express that kind of thing. There's no bitwise shift, modulo, or conditional operators. Great. Statements. Okay. An expression's main job is to produce a value. So expressions are things like this. This would be an expression, and this is a statement. So the statement is usually the thing that ends with semicolon. It's a statement is usually things like calling a function or assigning something to a variable, whereas an expression is just a thing to compute. Expressions. An expression followed by a semicolon promotes the expression to statementhood. An expression statement, that makes sense. And you can have blocks, curly brackets, we know these from Rust, that are sequences of statements. And so, for example, the way that you write a function, I would assume if we get there, is that the way you write a function is that a function is the function keyword followed by a signature followed by a block. Variables. Variables default to nil. They can be given an initializer. You can access and assign variables using their name. That makes sense. Control flow. If conditions, okay, so conditions are surrounded by parentheses. So are conditions in while loops. And we have for loops, okay? Functions look the same as in C and in Rust. You'd find them with the fun name of the thing, argument list, which has no types, so that makes it easier to parse. There's no named return type, and then followed by a block. Okay, and you can return inside of a function. That makes sense. And if there's no return, it implicitly returns nil. So unlike Rust, the last expression, a function is not allowed to, or a function block is not allowed to end in an expression and have that be the return value. Okay. Closures. Oh, it has first class closures. Closures are going to be their own kind of interesting thing to implement. So here you can see that add pair is actually a function. And so here we are passing add pair to a function as an argument. And so this function just takes a parameter whose type has not been declared at all and just returns that same parameter value. And so when we pass add pair as an argument, that ends up having this thing return add pair back, like identity. It just returns what is given. And so this ends up calling add pair. So this means that add pair is actually like functions are a first class type, if you will, in this language. This alone is not closures though. This is just first class functions. And then this is a closure. So you can declare a function inside a function. And crucially, the way in which that matters is like you see here, you can have a variable in an outer function, and you can have a function inside of that outer function that references variables that are declared in the defining scope of this function. And this is what is a closure. The nomenclature here comes from it closes over its environment. It gets to have access to the space in which it was declared, the scope in which it was declared. Okay. So inner has to hold on to references to any surrounding variables that it uses so that it stays around even after the outer function is returned. Yeah, and this is the other thing that's interesting here is that notice here, this is a thing that's actually kind of hard to do in Rust. It's not impossible, but it is hard, which is here we're returning this closure. And this closure captures this variable. And so that means that for this closure to be valid after this function returns, that means that this needs to capture this variable in some way, so that when this function returns, normally in Rust terminology, we would drop this variable value when this function returns. And therefore, you wouldn't be allowed to call the return value, the closure that gets returned anymore, because the variable it references has been dropped. But in locks, that's allowed. And this is basically because it has something equivalent to a garbage collector, right? It knows that the closure is still using this value for it to remain valid to access. And so therefore, it's fine to return this closure and then call it down here even after the function returned. And it also looks like print is maybe special here, that print is not a function. So you see print doesn't have any parentheses for calling print, but functions do. And so this makes me think that print is actually a first-class primitive in the language. So it is special. It is not just a function where you can omit the parentheses. Yeah, it's a built-in statement. Classes. Oof, it has classes. Interesting. Okay. Is it a class or a prototype language? Let's see. Interesting. Okay, so locks has classes, not prototypes. That's fine. So you can have a class, you can have methods on the class, and the methods on the class don't require the fun keyword. Okay. When the class declaration is executed, locks creates a class object and stores that variable in a variable named after the class. Oh, I see. So when we parse and execute this, when we interpret this class definition, then we create a class object and we create a variable that's named after the class. So we get a variable called breakfast that is itself a reference to the breakfast class object. So not an instance of breakfast, but the class itself. Interesting. Okay. And the way you create a new one is we don't have a new or anything. We just have a sort of implicit constructor that takes no arguments. Okay, you can access fields. That makes sense. This is how you refer to the current instance. And you can declare an initializer. You don't have to declare the fields anywhere. The fields are they just magically appear, I suppose. Great. And init is sort of a specially blessed method name that is used for instantiating things of that class. And we can have single inheritance. So a class can sort of extend another class. That's fine. Every method defined in a superclass is also available to its subclasses. And you can call supers init. Yeah, this is very standard Java version. Okay, standard library. A functionality that's implemented directly in the interpreter and that all user-defined behavior is built on top of. This is the saddest part of locks, Its standard library goes beyond minimalism and veers close to outright nihilism. Okay, great. That makes me happy. For the sample code in this book, we only need to demonstrate that the code is running and doing what it's supposed to do. For that, we already have the built-in print statement. Later, when we start optimizing, we'll write some benchmarks and see how long it takes to execute code. That means we need to track time, so we'll define one built-in function, clock, that returns the number of seconds since the program started, and that's it. Great. Okay, this is a standard library that will be okay to implement, I think. All right. Let's now, I'm going to keep that one open in a background tab to see where we go from here. Update. Ooh. An update during a stream. That's scary. Okay. How about, okay, empty file is going to be very easy, and then it moves on from there. There are a lot of challenges here. I wonder how far we'll get. They claim that these down here are hard, but I think they might actually not be that bad. Like scanning, I actually think Pratt parsing is going to get us through surprisingly quickly. Parsing is a little trickier. Evaluation. I think this is going to be fun. I'm excited. Okay, where's the start button? Start. Start building. Okay, welcome. Thank you. I'm going to do it in Rust. Thank you very much. Language proficiency. I'm going to go with advanced. Great. Next question. How often do I want to practice? Once a month. Accountability? No, thank you. I do not want accountability for my actions. Okay, let's go ahead and do this. Codecrafters Interpreter Rust. Codecrafters Interpreter Rust. Okay, push an empty commit. I believe in us. Git push. Origin master. Turbo test run. Oh no. We failed. Tokenized test locks. Expected line number 1 on standard out to be end of file null. Got nothing. That makes sense. Okay, great. Because we haven't implemented anything. Fireworks. Git push received. Activated. Okay. Comment the code to get you started. Uncomment the code and submit. Yeah, this is probably just a sort of tokenize. Oh, I see. Okay, great. So this is just, if the file is empty, then we just print the thing that the tester wants. Great, love it. Yeah, I did that. Okay, I don't. I'm confused. It uncomment the following code. There's some stuff at the top it wants me to uncomment too. Oh, I see. If I print to standard error. Why do they do this instead of just ePrint line? Can I just ePrint line instead? Feels excessive to be very explicit about writing to standard error. Right? I'm gonna go with this is probably better? Question mark? Great. It could be that I didn't know that was a thing. And now I don't need these things. Great. Git diff. No hacks. Git push. Next step. Test passed. Okay, stage marked as complete. Look at us racing through. This is easy. Read the instructions. Your task. Oh, interesting. So this makes me a little bit sad, but we might be able to We might be able to still do this with Pratt parsing. So this is where I'm gonna leave the challenge for a second, and I think I'm just gonna. I see. So the language sort of defines this sort of output for what it should look like as you walk through when you lex. That's fine. So this is just the lexing part. And the lexing is not where we need a Pratt parser yet. Let's see what the book wants us to do. Oof. All right. Filter, inverse, invert. Okay. In each turn of the loop, we scan a single token. This is the real heart of the scanner. It will start simple. Okay, it just... Yeah, we just walk one character at a time and keep track of every character and turn it into a token. Okay, so are there other files in here already? No, great. So I'm first of all going to start a lib.rs, and in here we're going to have a pub enum, which is going to be token. And then here we're going to use code. What's the name of this again? Codecrafter's interpreter. We're just going to use everything from there. And then in lib over here, we're then going to implement how do we want to do this easiest? I think we're just going to have a freestanding function parse lex, which is going to take any string. So the input here is going to be a stir, and it's going to return a result. And actually, if we want to be really fancy here, then we pull in a dependency on Miet instead of anyhow, because that way we can give errors that highlight specific parts of the input. Let's do that. Let's be bold. So Miet, which is 720. Okay. And I don't actually want this error for this either. And we're going to use Miet wrap error and error. In fact, we can just grab, no, I like having my own result. So we're going to do this, and it is hopefully going to return an impl iterator where the item is token. And so the other question we need to ask ourselves here is, do we care about this being streaming? Because there are sort of two ways to lex. One of them is a streaming lexer, where you walk the input, and as you get tokens from the input, or as you get characters from the input, you produce tokens from the output. So it's sort of a transformer of an input to output stream. The other alternative is to take the whole string, lex the whole string, and return, like, here's the vector of all the tokens I found. It's actually kind of tempting here to change this slightly and say that the input is actually into iterator, where the item is a character. And then what we're going to produce is an iterator where the item is a result of either a token or an error. With a sort of, once the iterator returns error, it will only return none. Right, so the idea here is that we're going to be grabbing characters from the input, trying to lex them. And whenever we successfully lex a token, then we yield the thing from the outgoing iterator. Ultimately, though, either we successfully yield a token and then we keep going and we successfully yield another token, or we might yield we might end up basically with a lexing error. Like, for example, we encounter a character that wasn't supposed to be there, that we weren't expecting in the input, at which points we will make the iterator then return an error. And from that point forward, the iterator is sort of invalidated. Because now what we can do is we can say input is, and this is where usually I think you might need a peekable here, but we might actually not. Someone said, don't you also need a wait state? And the cool thing here is, yes, you kind of do. You need to sort of accumulate characters. But at the same, I guess really what we want here is a generator, right? We kind of want a generator here. You can, however, do this by doing, like essentially what we do here is we define a struct that is sort of the lex state, right? And that's going to hold something. And we are going to do at mute lex state is a lex state of nothing. And then we're going to do I'm trying to see if there's a smart way we can do this here such that it's actually a lazy iterator. Because the problem, right, is that you might get one character and then you might get another character that should be a part of the previous token. So the first thing doesn't yield anything. And so that's sort of trivial to write with a while loop, right? The problem with a while loop is what you really want to do is like for C in input, do some stuff. And one of the things is going to be, if completed token, then you want to yield, which is not a thing. We don't have generators in Rust yet. Then you want to yield token for C so far. But we don't have a way to express that in Rust today. The closest you can do is you have a struct that sort of holds the state instead. And then the way we're going to do this is we're going to do here, new over input, and then we're just going to return that. You'll see how this works in a second. And then we're going to impl lexed, I guess really lexer. And at this point, we don't even need the function. We're going to have a new that just takes this and returns the self. And then we're going to implement iterator for lexer. Where the item is going to be this. And this, of course, is going to be a to-do. But one of the things we're going to have to keep in here is this is going to be generic over the iterator. This is going to be I. And this is going to return a self where the iterator is input, or is input dot into iter rather. And then here we're going to return where I is an iterator whose item is a character. Great. And of course, this is going to be public. That's public, and the iterator implementation is automatically public. And then in here, next, this is where the actual lexing is going to happen. So whenever we get asked for the next output token, that's sort of what this is asking for. Like, what is the next output token in the stream? Then we need to figure out, okay, what is the next output token? And that's going to depend on what the inputs are. So in the call to next here, we basically need to figure out the next token. And the way we're going to do that is while let some C is self.iterator.next. We might actually not need any other state in the lexer than the iterator. We might be able to just keep it as local state in the next method. Okay, so the question now is, how do we lex? Well, C here is going to be a character. And the thing we want to match on here is we want to sort of construct up. Here, if we go back to the things that we should be able to lex, and this is where I want to see the list of all the tokens. Okay, so here are the base tokens for the language. Now, these, of course, are slightly different in Rust. The syntax here is going to be this, and this is going to be token. Okay, now for all of these ones, we actually just want to return some of this. Right? None. And in fact, we can do let sum is this, and then we can do question mark, because if the inner iterator returns none, then we might as well just return none ourselves. This is actually a little bit special because it might be later on here that if we get an open double quote, for example, and then it's the end of the input stream, then at that point that's actually an error. It's an unterminated string literal. But we'll handle that in a second. And so now we want all of these to be variants. Great. So all these are now variants up here. And we can also get help from Rust here to rename all of them. Why is it okay with these? Oh, I think I've seen a bug report about this, and it's actually kind of annoying to fix. Me colon and tar. And then we want to implement display for this so that people can print tokens back out, which is what we're going to want to do in order to print this whole output that it's looking for. Remember how it wants a very specific output of which tokens were found? Well, we're going to give it to them. So we're going to match here on self, and this was left paren, and this can actually just be right f, and this and that, and then this is going to be right paren, this is going to be left brace, this is going to be right brace, comma. There are crates that can help you do this a little bit with less boilerplate. In practice here, I don't think it would be worth even finding one and setting it up, because it's not that much work, right? Star. Okay, so now we have these tokens. And we can also derive debug. We can derive partial eq and eq, and we can derive hash. And in fact, we can also derive clone and copy. No, not copy, because we're also going to want to support literals here. And in fact, this is one of the reasons why it might be a little annoying to do this token down here over character inputs, because it means that if you, for example, want to parse out you want to tokenize something that has a string literal, then what we're going to do here at the moment is we're going to parse out every character one by one, which means we're going to reconstruct the string one character at a time. So it's going to be slow, but it's going to be possible. The alternative would be for this to take a stir with some lifetime, and then you return a lexer with a lifetime tick A as well, so that it can refer back into the string. That's actually pretty okay. This is how Serde works, for example, is that the deserializer has a lifetime bound of the input precisely for this reason. And in fact, maybe that's something we want. Now that I think about it, maybe it's not that useful for this to be an iterator over characters. Yeah, maybe we actually do want this to be a... All right. Okay. I'm sold. And in fact, we can sort of follow the Serde nomenclature here. And say that you need to give me a DE, and then that's going to return here. And the iterator here is actually going to be rest, where rest is sort of the remainder of the input. And this is now going to be over DE. There's no longer generic I. This is just going to be a DE stir. And the reason I call rest here is because initially it would be the whole string, and then once we've read the first character, we're actually going to move the string reference, the start of the string reference, so that it points to the remainder of the string instead. And the reason we want to do the D here is now token can be given a D over here. So this is giving me generic over the thing that's being deserialized. And so now once we get a string literal, for example, in here, literal, then that literal can actually be a D stir. Now, you're going to see this in a minute when we get there. You can't always use this as a string reference, because sometimes you need to do de-escaping, for example, or unescaping, right? Where if there's a backslash in there, you don't want to preserve that in the literal, but we will not deal with that right now. So for now, we're going to stick with this. And so now what this is going to be is if... no, we're going to do self dot rest dot how do I want to do this? I want to do split So I can write it the sort of dumb way first, which is chars.next. And then I think there's like chars. Yeah. And then self.rest equals self.rest from c dot is it bytes. What is the name of the method on characters? Characters. Len utivate. Like so. There we go. But I think there is a way to do like split at oh, it's a split add and a byte index, which isn't quite good enough. Okay, so what we're doing here is we're pulling out the first character of the string, and then we are that returns an option. If the string is empty, that option will be none, and so therefore we return with a question mark. So C here is the first character that we haven't lexed yet. And then we reassign rest to point to the remainder of rest. So we sort of bump the start of the slice pointer. And now we can match on these. Now this is dot minus plus semicolon and star. And we also have to remember that this is actually okay. Like so. Because again, remember, we can return an error at any one token that we're walking. Oh, Cars Aster. I don't think we can use Cars Aster because I think its lifetime is tied to the lifetime of the iterator. But I could be wrong. Let's try that. So cars is self.rest.cars. And then C is cars.next. And then self.rest is cars.aster. Oh, great. Aster returns a string whose lifetime is tied to the original input string. Perfect. That's what I wanted. That way we don't have to do any of our fancy UTF-8 bits. Now, the reason I want to specifically return here is because there are some characters for which we're going to fall through, such as open double quote. For those things, we don't want to return. So it's specifically these we want to return early, and anything else we actually want to fall through. So for now, what we'll do here is we will return, and this is where Miette is fun, because we can do Miette bail. And technically, what we would want to do here, I'll actually keep whole here. So whole is input and rest is input. There we go. And then I also want to keep track of the I that we're at. So initially we're at I0, or I guess this could be byte. Oh, it might not be byte. It might be, yeah, it'll be I. So this is like, what character are we at? You'll see why in a second. So this will be self.I plus equals 1. So if we look now briefly at Miette, you'll see that in Miette, when you output an error, where's Miette bail? Bail. That is not the one I wanted. Miette. Where's the actually useful one? Diagnostic. Okay. Yeah, so you can give, I think Miette had the same description. So you can give a severity, which is fine, and code and help and stuff. But the interesting thing is how this is rendered. So labels lets you label a particular subset of the input and say, this part of the input is the one that's interesting. So I think if we go to report maybe, and then diagnostic, code is the one that I want. Labeled span. Oh, it is byte offset. Great. From the beginnings of a source code. Okay, so we do actually want byte offset here. And so then this will be c.utf8, len utf8. Technically, we could write a reader that keeps track of how many bytes it has yielded and stuff, but that gets a little too annoying, and I don't think it's going to be all that useful. But what's cool here now is that if we now go back to I need to keep better track of my tabs in delayed source code. No, I don't want delayed source code. I want the one where you actually give the source code directly in. Aha. Source is what it's called. But I want to do it with the macro instead of having to construct the big type. Because snippets is the thing that I want. I forget how you pass this to the macro. I don't want to use the error type. That's frustrating. Oh yeah, you're right. It is just with source code. Yeah, right here. Okay, great. Okay. And then I'll have to grab labeled span. Some error of this. Self.whole. Expected literal, right, because I also need to give here, I want to say unexpected token in input. Does that really need to come first? That doesn't seem right. But here we can then do self.byte. I guess actually we want to do this here. Self.byte to self.byte plus c.len utf8. This character. What am I doing wrong here? Oh, len utf8. Oh, and this probably has to be toString. Now is it happy? Maybe. Yeah, and then double quote, for example, is going to just pass through. Okay, fantastic. Implicitly returns nothing as its body has no tail expression. Right. But there's a question mark right there. Right, and I don't have I need to do over here. Okay. So now we have a lexer that will at least recognize these tokens and produce them as we see it. And so now, I mean, we can try this out in our main, right? So down here, we want to say let lexer is, or mute lexer is lexer : new from file contents. And then we want, what was the output structure that they wanted here? they wanted they wanted the type and then the contents, and then what is this last thing? Are they all null? Oh, it's interpreted value. So I'm guessing for strings. I see. Okay. Yeah. Great. So what we'll do is for token in Lexer, we will do print line. And I think we'll just straight print out the token and expect it to follow the sort of format that they're after here. And so this means that we have to make this slightly more sophisticated. So for a for the punctuators, you see it just prints the sort of the raw character, if you will, and then the last, I guess, then is the literal value, right? So that means left paren should print this, right paren should print this, left brace should print this. Wait, what kind of brace? And that kind of brace. Okay. Null, comma is comma null, dot is dot null, minus is minus null, plus is plus null, semicolon is semicolon null, star is star null. And so if I now run cargo R, and in fact I could take this, and then I'll actually run it with echo, and I will echo with -n so we don't get a new line at the end, and psub, which gives me a file for something I print. Let's see what happens. Parameter DE is never used on line 5 in lib. That is because we don't actually have strings yet. So we're going to need string, which, just trust me on this, is going to need to be a cow stir. But I don't think we actually... Do we want to implement the parsing or the unescaping proactively? I don't think so. I think that's just going to be this for now. And so string is an example of something that will have a value. So if we go back here to string, great. It will print string, and then it will print this. So actually this one will be a little more convoluted. So it will return write f this. And then the last bit here is actually going to be a little tricky because it's going to be unescaping the string. And so here, that last argument is going to be unescape. Escape s. Where unescape is, I guess we'll put it on Lexer, or we'll put it a token maybe. So we'll have down here, we will impl token, and we'll have a pub fn unescape, which takes a stir and returns a cow stir. So it does actually need this to do. Right, so the idea here is that it is going to take some potentially escaped string, and it's going to return either if there's nothing that is escaped in that string, then it'll turn just a reference directly to the input string, or if it does need to do some unescaping, like removing backslashes and the like, then it will have to allocate a new string and move it over. And the reason here for the tick underscore on token, but the D here, is that this is not really a method on token, right? The S here is not really tied to the lifetime of token here. It's just tied to the lifetime of the input. I think technically we could do this. It's just a little weird to me to write the signature this way because we don't actually care about the lifetime of the token type here because it's a static function. And for now, we have not done S yet. So for strings, we're going to do that. And then for numbers, similarly, we're going to actually print them out. And main is still unhappy because that token is... And so we're going to have this also return a miet result of nothing. So this is going to do miet bail. And here too, we could really use clap instead of this weird interface they've set up. So that's probably a thing we'll do next, which is, let's just do this properly from the beginning. This is one of those where we're doing a bunch of work up front here. You could probably just walk through the challenges, but instead I want to do it kind of properly. And then we can sort of fly through the challenges later on. So over here and down here, we're actually going to say for arguments, we're going to have a subcommand. And I think there's a subcommand example over here in the tutorial. Subcommand, great. So we're going to get rid of these other things from the original. We're going to bring in here subcommand from clap. And then down here, we're going to grab this example, put it down here. So the commands that we have, at least initially, is we just have tokenize, and it has a single file name argument. So file name, which is going to be a path buff. And I know clap is very unhappy with me because I haven't added it yet. So we're going to do cargo add clap with features derive. And then now all those errors should go away. And this needs to derive debug. Okay. So now we no longer need this return value here because clap takes care of it for us. The command doesn't need to happen anymore. We can now match on args.command directly. And if that is commands tokenize, then we get the file name in directly. There's no need to match on anything else because clap takes care of exiting if we need to. And at the end here, we're just going to stick in an OK. So the compiler's happy. We're actually going to not allow this to be an option. We're going to require a subcommand. And here, instead of this sort of read to string with an unwrap or else, this is one of those places where we can make use of miet wrap error, which lets us do this. Wrap error. In fact, we can do wrap error with. Format, reading file, failed. Reading, what's the file name here? File name. And because it's a path, we have to do .display unless we brought in a crate like Camino, which we're not. So like this. And it's unhappy with me because dot into diagnostic. This is the one thing that is a little annoying with Miet is you have to specifically call this function to turn non-Miet errors into Miet errors so that you can then wrap them, which is not something you need with anyhow. If you're using anyhow, you can do this wrap error with as well, except it's called context with. Okay. Now we have the Lexer. We don't need it to be mute because we're just looping over it. And in fact, we can even go all the way to this. Okay, let's see what happens if we try to run it. On recognize command, that is because we need to say tokenize. Okay, so we don't need this ePrint line. That's, can go away. So now it found in this input string that we get left paren, left brace, right brace, semicolon, comma, plus, minus, star, and then we don't have anything for this. And you see here, the error that we got out here says unexpected token and input. I'm looking for fancy error reports. I got to install Miet with a fancy feature. Okay, cargo add Miet features fancy. Why? Oh, I remove cargo lock. Try again. Great. Okay, yeah, so see here, although the location is completely wrong, but we got a fancy error message that showed the input and then tried to highlight which character had the bad thing, but it should have highlighted this exclamation mark right here, which is not what it did. So our Lexer is wrong. So I think we are doing something wrong with self.byte. Oh, which is we're not incrementing in this case. So I think we actually do need to move this up here, and then this needs to be self.byte minus len utf8 to this. Whoops. Like so. UTF-8. Great. So it said this character is, so we could even here say unexpected token boom. Unexpected token exclamation mark and input this character. Okay, so now we have like slightly nicer looking output messages, and this error we sort of just get for free now as we write more stuff in the tokenizers. Okay, fantastic. What's next? Well, obviously there are more things we need to parse here. So if we go back to the LOX language, it's actually easier to just walk through the scanning test to see what the different identifiers are. I guess most things here are just going to be identifiers, which is going to be a little interesting. Let's handle all the special ones, which is going to be, and I'm actually going to be a little fancy here and say group, which is going to be string. So here we're gonna sort of say maybe started is better. So we're gonna return here what we have started. I guess we could instead return just the character, the delimiter. The reason I don't want to do that is because if we do, we would need to match on all possible characters later. I would rather it tell us whether we've handled every case, right? So now we can do, I guess it's this, and then it is 0 to 9, which is number. So these are multi-character literals or multi-character tokens, right? So number, string, bool? Are booleans? No, I don't think booleans are. I think it's ident. So here it's going to be from A to Z or underscore, which are started ident. Wait, why is it not letting me do that? Oh, because these are characters. So double quote starts a string, 0 to 9 starts a number, A to C and underscore start identifiers. Right? Yep. And then there are also keywords. So these are keywords that we're going to have to parse. But keywords are just identifiers. So that one's easy. What we're going to do here is actually we're going to pull out, we're going to match on the identifier that we end up producing. And if it's one of these, then we will handle them. So an ident is going to be a D to stir, and a number, specifically it said in the spec, was always a double precision float. And then we're going to want to handle these as keywords. I don't know why end of file is one. That feels kind of weird. But and class else false for else false for fun. If nil or turn super this true var. I'm sure there's an easy macro for this, but it's easy enough to type out. End of file feels wrong here. This feels like end of file should just be printed like this here. Shouldn't be its own token. Oh, and because there's an F64 in there, we can't implement eq or hash because floating point numbers are no fun. Okay, and now it's going to be mad at us if we don't put in the other arms. Oh. Why on earth did it decide to stick them all in one line? That makes no sense. Okay, I think it's this macro that it's getting it all hung up. So what we're going to do is we're going to do this and see if it... Why is it very unhappy with me? Okay, we're going to go back to what we had before. And then we're going to... as much as it makes me sad, we're going to do this. This I could have search replaced, I realize, but where's the fun in that, you know? Okay, and now this can go away, and this can go away. Why is it... I've done something to make Rust Analyzer unhappy. This doesn't need to return anymore. Like somewhere I have a syntax error. Aha. There we go. Now it'll format for me. And so now I can go here and tell it to please add the other arms. So an ident, we're going to write out as F identifier. Why don't you return the string from match and then write? Because that doesn't work for things like this, where it's not just a single string. So for identifiers, I guess it'll be I and null because they don't have a value. And for numbers, it'll be F. I think for the number, it seems like there's sort of a requirement that we're supposed to give the original literal. So I think we might need the literal and the string, the number in here, so that we can sort of accurately represent the input that we were given. So this is then, if we go back to numbers. So is there an example of these being different from each other? Yeah, so 456, for example, its value is printed as 456.0. So that means this will be number, then it'll be the literal, and then it'll be the n. And then this is just... I don't think we need debug even. I think we just print the literal here. And then here, this is F. What is the keywords? And null. And then it's this for each of these. Actually, yeah. Okay. We're going to do this. Love macros. Now, what I wish was that there was a... There is, I'm pretty sure there's a Vim thing for uppercasing or lowercasing a string. But because I can't remember it, I'm just going to do it manually. GU motion. Oh, yeah. Is it GL motion too then? GL motion? GU motion. Aha! Great. That's the one I was looking for. Thank you. Okay. So now we write out all of these, hopefully correctly. We still have a bunch of these that are missing, which is fine. And we still have like exclamation mark, and that's because those are here, right? So we're still missing some. We're missing bang equal. Oh, bang equal is a single token. So that's also interesting. So that means we have to be a little bit sophisticated with some of these, right? Because it's not like a single equal is actually... Oh, a single equal is not here. That is probably considered a... Wait, where is single equal? That seems weird. This doesn't test for single equal at all. Unless I'm just blind. Huh, interesting. Okay, but we do need to then add some more tokens to this. In particular, we need up here, we need bang equal. We need equal equal. We need less equal. We need greater equal. We need... we don't need bang equal again, but we need less, we need greater, and we need slash. And then this is going to yell at us again, so we need to fill those in. It's easy enough. We'll move those back up to where the other identifiers are. And then we will do this. And then we'll do this. Actually, we can do... I was a little sloppy in my definition there. And then I guess these have to be with underscore. And also bang equal should be this, right? It should print the actual literal representation, which is easy enough. Now, there's an interesting question about whether white space is allowed here. So, for example, for less equal, if someone in source code form writes less space equal, should that be tokenized into less equal? And if so, should this print this? If so, that's totally doable. It would just require that the token always keeps track of its underlying literal, which we could do by just having a struct that wraps the token that holds the original literal and then the token enum value. Okay. And slash, of course, should be slash. And so now down here, we have a couple more things to handle. We have, nope, not that. We have less, greater, and slash. So slash is easy. Less is started less. Greater is started greater. And this is started bang. So it's less, greater, bang. Did I typo something? You duplicated left paren and right paren. No, left brace and right brace. This is because in format strings in Rust, this means print out the value of variable foo. It's like string interpolation. But if you want to write a literal open curly bracket or close curly bracket, you need to write it twice. That's how you escape it. Okay. So now we have some things that can be started. And then I guess we want to match on started. If we started a string, we want to do something. If we started a number, we want to do something. If we started an ident, then we can do that later. If we started a less, then I think what we want to do is if rest.starts with equal, then we return sum of token less equal. But we also need to advance rest by 1. And we need to advance byte by 1. Self.byte plus equals 1. And self.rest is self.rest 1. See, I also thought we needed an equal, but starts equals. Yeah, you're right. We need an equal for if we start an equal. So if self.rest starts with equal, then we return a less than equal here. Yeah, you can do 2 characters reading too, but it doesn't really matter to me. If the next character is not an equal, then we simply return sum okay token less. And then for greater, it's going to be the same thing. And, we could tidy this up a little bit, but I'm okay with it. So that this is greater equal, and this is greater. And then for bang is the same thing, where if it's an equal, then it's a bang equal. Otherwise, it's a bang. So that sounds like there really should be a bang token, but I don't see one, right? I only see a bang equal here. But the reality is that there are bangs in the grammar, because you can have a not false, for example, which doesn't seem to be handled at all by these tests. And same with single equality, which is used for variable assignment. So I think sort of in preparation for those, we're going to add standalone bang and standalone equal. So bang and equal. Couldn't it be like a state machine? Yeah, it is sort of a state machine here. It's true. And in some sense, that's what we're encoding here. We're just manually unlooping it in a sense. Okay, so bang. And then we also need to do the same for equal. I guess actually what we could do here is we could instead say or equal, where or equal holds a token and a token. Oh, but we can't use generic parameters. That's fine. We'll do that. Because that way we could change this to be, this is or equal of token less equal. So it's not really or equal. It's like maybe equal, where this is a, it's if equal else. That reads better. If equal else. So if equal, then it returns less equal. Otherwise, it returns token equal. No, token less, right? Greater than is if there's a, if the next is an equal, then it's greater. Otherwise, it's this. Bang is bang equals. Otherwise, it's bang. And equal is equal. Otherwise, it's equal. Bang is exclamation mark. So now we can just say if equal, else, yes and no. So if this, then it returns yes. Otherwise, it returns no. And that way we avoid all of this duplication. And that makes me very happy. Like so. Fantastic. And in fact, this doesn't need to return at all because we can do this. All right, beautiful. Okay, so now we might as well just look at the others too, right? I guess white space is one we haven't covered, which is see if c dot is white space. What do they want for white space? Space? Oh, white space should just be ignored completely. That's interesting. So is white space, then so this means that we actually need a loop around this whole thing, because if there is white space, actually no, we can be even fancier. We can say let curlen is self.rest.len. And then we could do trim, which is we do self.rest is self.rest.trim start. And then we can say self.bytes plus equals self curlen minus self.rest.len. And then we can say, yeah, so this trims off the white space before we look at every token. And that way we don't actually need a loop. It's a little bit weird and wasteful, right? Like it feels like, given we have to match on it down here anyway, it feels kind of odd. I think I actually prefer the loop version. I think we're going to do the loop version. Go here. And so this now is going to be a break with whatever this is. Oops. So if we hit white space, we're just going to continue through that loop. And started, I can just stay defined there. And then this guy can actually go out of there. We don't need to reconstruct it every time. And this reassignment is fine because this doesn't actually borrow self.rest, it borrows the underlying string. Nice. So we do then need to be a little bit careful here with this code. So this is trim start dot starts with. Then it is dot trim start this. Right. So this way we'll actually trim the things that come before. What makes this awkward is that it does mean that if we get in, so we need to decide here whether we want to actually keep the original literal for every token. And I think we might have to, which is not lovely, right? But it does mean that we would do this, and then we would have a pub struct token, which has a kind, which is a token kind. It is a kind, which is a token kind, and it has a origin, which is a D8 stir. And now I think now the token kind doesn't need a lifetime at all, because for string and ident and number, those are all just captured by the origin. So string is just, this is a marker that this is a string. An ident is just a marker that it's an ident. And a number is just a marker that it's a number and the interpreted value. For strings, we don't actually interpret the value. We could have this hold the thing that we've sort of unescaped from the beginning, but I think I'd rather parse it lazily, actually. So then, now what we want is we can match on self.kind, and then for all of them, we're actually going to print here I as self.origin, and the reason I want this to be I is so that I can do this. Right, so for all of these, it should be the case that rather than hard coding what that was, we want the original input that was parsed to yield that token. And so that way we can, if that internally contains some white space, we will actually preserve that white space. So now this now needs to unescape I instead. And all of these are now token kind, which is easy. So ident and n, and this is now I. And then if we don't want that to be I, we can make it be literal. It's not really a literal. I is fine. Or I guess origin is maybe nicer. And it can't be self.origin because that won't work with string interpolation in this nice way. All right. So now this gets a little more awkward because this is now for these, we actually want to capture what the origin is. And the origin is a string reference, which we don't get out of characters, but we would get out if we did, what is it? Chars indices? So that then returns here. So C now is at and C. And so at is the byte position of the character. And so then we could do, so C stir is self.rest from at to at plus c dot len utf8. Like so. So now we have the c as a stir. And then for these, how do I want to do this is the other question. Because this is getting ugly real fast. But we could actually do this with a... yeah, we can have a little helper function here, and we can just define it in here if we really want to. So this is going to be just, we're going to call that, and it's going to be a token and origin, and it's going to give us back a self item, if I'm allowed to refer to that here. All right, fine. I'm going to give you back this. But it's actually going to give you, it's going to take a token kind, is sort of the thing that's going to save us here and give us back that. And inside of here, it is just going to return sum of OK of token of the kind and the origin. So is that worth having the function call? What it'll look like is this. That versus yeah, it's nicer. Okay, great. So for each of these are now going to be just. Actually, a closure would work here pretty well too. Let's do a closure. I agree with you. Because the closure can capture, let just is, it's going to take a kind. It can be a move closure, that's fine. And it's going to return some OK token with the origin is cstir. Good call. Closure is nicer here. And these are all kinds now. Beautiful. Beautiful, beautiful. So this and kind and kind and kind and kind. And this indeed should be kind. And now started doesn't need a lifetime. Beautiful. Oh, so good. Looking so nice and clean and crisp. Okay. So this now needs to be a little more interesting. So the span of this token that we're reading is actually self.rest from at to something to the self plus. This is also wrong. We kind of need to know how much we've read out of rest, which is going to be I think we can actually just say rest, self.rest is self.rest.trim start, but that's not quite right because we need span is self dot, because rest here is already moved past the characters. So I think we're going to sort of buffer here as well. C onwards is self.rest. And then we change rest. And then here, the span here is going to be oh, this hurts my brain. We're going to do self.rest is self.rest.trim start in case there's any white space. And then we are going to say that and then we're going to say, because now we have I wonder if there's a function in for a slice. Like, remember, the C onwards here is it includes self.rest. We know that, but the compiler doesn't necessarily know that these are pointed to the same string. So what I'm wondering is whether there's a function in the standard library that lets you compare two strings, and it basically does like a pointer comparison to check if one is within the other. This is actually I'm going to try something, see if I can express this. So I want a stir to stir. I want to stir and stir to usize. Maybe it's U8 actually. Maybe it's defined on, or maybe it's defined on any T to usize. Maybe it's only on U8s then. That's fine too. Option U8. Option usize. Fine. I guess I will just look at U8. Fine. I'll look at slices. Slice? In names. Slice. Thank you very much. What is it called? It's not that. Should not require unsafe. No, I don't want to use pointer equals. It is a very specific function. It might not be there. It's not a line 2. It's not a SIMD. Not is sorted. You might be on U8. No, maybe it's just not there. I feel like it should be in there, right? Because what I really want here is just to say, give me the difference in the start of these two slices if one overlaps with the other. But I guess it will not let me do that. So instead, I have to say let trimmed is self.rest is C onwards .len minus self.rest.len. So that will be how many characters we have read out of rest, including the trim, plus 1, which is the character we're about to read. No, I guess trimmed -1. So we don't count C. And then we do self.byte. Do we need to eat the white space here? We don't. So it's only really... But because we might as well trim here. There's no reason to not do it here. So self.byte plus equals trimmed. And then in the case where there's not an equal sign next, then we return OK of token, where the origin is just C string and the kind is token kind. No, it's just no. In the yes case, then the span, then we can just continue to use self.rest. So if self.rest starts with an equal sign, then the span is then self.byte plus equals 1. That I already have that down here. Self.rest is self.rest incremented by 1. And the span is now C onwards, right? It's C onwards, starting at which is the location of C. I guess we could rename it C at. Why do we even need the at here? Yeah. Which I think is just 0, right? At here is guaranteed to just be 0. So I think this can just be until, and in fact, I bet you that's here too. We don't actually need at because we know at is 0. Oh, we don't, because, this is actually a bug that would hit us later anyway. Because we're not reassigning this at the start of every loop, its counter is going to be out of whack because we're resetting rest here. So I think we do actually want it in the loop. So note, this must be in the loop for the indices to match up with C onwards. But now we're guaranteed that at is 0. I think. There's no way for it not to be 0 here, because we're just taking the first character. So I think that means we don't need at, which means that this can just be at to c.len. And when we get further down here, we know that it's C onwards until, and then this is going to be C len utivate plus trimmed plus 1. Right? So we grab all of the length of C, we grab the trimmed white space, and we grab the 1 byte, which is the equal sign, and that's going to be the span. The rest here is going to be just updated by 1 because it already points past the white space because we moved it here, and it points past C because we moved it up when we read C. So byte only moves by 1. And then here we return token where the origin is span, and the kind is yes. Now the other bit that's interesting here is this is where smarter people than I would, instead of inserting a string reference here, you would actually just keep the byte offsets here, so that you don't have string references to the same input string everywhere in your program. You just instead just keep around the the byte offsets, and you can compute the strings later. In fact, that might make it easier because we don't need to do all these like string slicing, but I'm just going to keep it this way so that we can print them easily. Okay, what happens if I run it now? Okay, now it gives us something that looks pretty reasonable for that input at least. And if I now try to do something, in fact, yeah, it got bang equal, it got equal equal, it got less equal. So what now if I just add an equal in here, then it gives us indeed, that's just an equal. And if we add a bang in here, it adds, ooh, it made that a bang equal. Why? Oh, because I did add it, in fact, before an equal. If I'd have added after, it's just a separate bang. Okay. There's something wrong about our print though, because this just prints equal when it should be printing equal, and this needs to bring bang. All right. And then, okay, we're on a roll. So how about we just keep doing this while we go here? So we might as well just do numbers because numbers are easy, right? If we find something that starts with a digit, then what we want to do is we want to find, and this too is a question of like, do you allow spaces in number literals? I don't think so. I think you disallow spaces in number literals because that is one number followed by a different number. Unlike less than equal, where I feel like a space is probably okay, even though I'm tempted to just disallow it. Oh, can idents have uppercase? Probably. Probably. You're probably right. Disallow spaces, allow underscores. Now that's the power move for numbers. I agree. I like that. But it still has to start with a digit, right? Same thing with dots. You can't start a number with a dot. In Rust you can, but it's fine. The nice thing here is that we don't actually have to parse this ourselves. We can be a little bit smart about it. So here's what we'll do. We will say that if we have started a number, then we have to read until we no longer have numeric characters we want to allow in numbers. And so that means we're going to do self.rest.find C. We're going to find the first C where either C is equal to dot or C is or actually we're just going to match, or we can even do better. We can do matches C of either a dot or an underscore or 0 to 9, right? Isn't it position? So we're already checking that it's starting with a number. So that check is up here. So we want to find the first dot because we only want to allow one dot in the number. Because if you write something like 123.456.789, I think that should parse as, logically speaking, 123.456, and then a dot, and then the number 789. Right? I think that's what it should parse as. And so therefore we need to find the first dot, and then if till first dot, and then if self dot, and here too we need to be a little in the case where we don't find we don't find anything that is allowable in number after the first one, then the number is just the very first digit we got. So that's an easy case where we can just return with sum of OK of token of where the origin is C stir and the kind is token kind number. Easy peasy. Like so. And then if self dot rest, and what is position again? It returns. Oh, I guess it's cars is what I want here. But I think there's a. Isn't it find? Oh, find does return the position. Okay, great. If self dot rest till first dot plus one starts with a dot, or rather, if it doesn't start with a dot, then we're also in an easy case, because in that case, we just say that the thing to return is C onwards until till first dot. It's C dot len UTF-8 plus till first dot. And in fact, here, if we want to help ourselves a little bit, we can search including C, because we know the first thing is the digit, so that way we don't have to like splice strings. So then we can do C onwards here as well. And then this is just C onwards till first dot. The reason here is if there isn't a first dot, then the first thing that this... Oh, I guess this is find the first that doesn't match this. Yeah, so this is going to be it's going to return the position of the first non-numeric character. No, that's not what I want either. I have to think here a little bit, because what we kind of want is to find... Oh, actually, this is way easier than I think. I think this is going to be just last non-digit, or I guess first non-digit. Yeah, this is just me being silly. So that's going to be the first non-digit. And then what we want, so then this is also wrong. This could just be we got to the end of the string without finding a non-digit. So this is actually C onwards. And maybe for numbers, we should also not parse them until like on demand. But the number is going to be, we're going to parse it right here. And if it's a number, then we're good. And if it's not if it's a parser error, then we again do a nice miette thing. We'll fill that out in a second. I wonder, can I make this a... Oh, right. It has to be a... Return some error yet. Because then we want to highlight that this is not a valid literal. And actually, I can make this a lot nicer by just saying unwrap or else c on words.len. Because it's going to share the same logic anyway. Now, the interesting part here, there are a couple of interesting parts we got to figure out. The first one is, so the thing to parse, so the actual literal is C onwards until the first non-digit, right? Logically speaking. However, it's not actually quite that simple. The reality is that if the literal has multiple dots, then we want to shorten the literal. And so this is where we're going to do dot split n 3 dot well, I kind of want to I want to skip the first dot. Yeah, so one way to do this is you find, you don't search for the dot here. You search for just underscores and numbers, and then you see whether the next character is a dot. And if so, you do the same thing again, and then you add them together. And okay, I guess maybe that's easier than trying to, because the other alternative is that you, now that you have the literal, then you shorten the literal to the second dot if there is one. Right? And I don't know which of these is easier. I'm tempted actually to just say, we're just going to say, oh, we're not supposed to parse the float yet? All right, fine. No, we must be supposed to, because otherwise you can't print out the number here. So I think you need to store both. Otherwise you can't print out the thing that you just parsed, or lexed rather. So I think I actually do want to do the split here. And then the way that I want to do it is, is there a literal dot? What does split terminator do? No, that's not what I want. 1 is dotted dot next. 2 is dotted dot next. Actually, and then here's what we do. Dotted dot next, dotted dot next. Yeah. This is actually going to be pretty nice. So if we have Yeah, literal. Yeah, okay. Two. Hopefully you can see where I'm going here. So if we have all three, that means that there's multiple dots in there. And so the actual literal we want to give is a slice into the original literal here, only until 1.len plus 1 plus 2.len. And if it is this, then we can just return all of literal. And if it's anything, in fact, if it's anything else, we can just return literal. And so we can even actually do if let this, then literal is this. Right? So we try to split the numeric literal into 3 parts. So that would mean 2 dots, right? Splitting into 3 parts is 2 dots. And then we look for, if we have all 3 parts, that means there are at least 2 dots. And so in that case, we want the literal to only cover the first and the second part, meaning the thing before the first dot and the thing between the first and the second dot, and the one in between. And so now we can say self.byte plus equals literal.len minus c.len UTF-8. Right? So we add the additional characters that we read, and self.rest is going to be self.rest from the extra bytes we read. Extra bytes onwards. And now we can match the literal, or we can parse the literal. And if the literal gives us any trouble, then we can give a nice error message. Oops. I copied too many lines. We can give a nice error message that says at numeric literal and then we can just this. So if the literal fails to parse, then we give a nice error highlighting the numeric literal that they tried to give us. Otherwise, we give back the token. Let's see how well that works. So let's try it on, let's just try that the original works. Great. So if we now try a couple of numbers, so we try 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3 underscore 4, 5, 6, dot 5, 7, 8. What am I saying? 5, 7, 8, 7, 8, 9, 1, 2, 3 dot 4, 5, 6 dot 7, 8, 9. Well, that wasn't quite what I was hoping for. It got the first and the second. It didn't like the third, and it did not give us a nice error. Why? Literal is... psub is a really handy command that if I do echo foo, it just prints foo. If I do echo foo to psub, this is a this is a fishism. The equivalent in Bash is this. So I'll show you in a second. So if I do, oh, it doesn't work outside. So if I do cat, so cat prints out the contents of a file, right? Let's say that I want to echo something, but I want a file name that holds that contents. Then I can do echo foo psub. And in fact, if I do echo, you'll see it gives me like a temporary file name. In Bash, you can do the same thing. So in Bash, you can say echo foo. And you see it gives me a file descriptor that holds the output of the process inside of there. So if I run this again, what does it tell me? It found a literal 1, 2, 3, found a literal 1, 2, 3, 4, 5, 6, and found a literal that, which is the correct literal. So it extracted the right part, but then wasn't able to parse it. And the reason it wasn't able to parse it, I'm guessing, is because the Rust parser for floating point numbers probably doesn't accept underscores, even though Rust itself does. And so I'm just going to remove that from here, as sad as it makes me. So now this. Yeah, so the last one we had that has 2 dots gives us 1, 2, 3, 4, 5, 6, followed by a dot, followed by 7, 8, 9, which is a number. Great. What if there are multiple consecutive dots? Shouldn't be a problem. Let me do 1, 2, 3, dot, dot, 4, 5, 6. Oh. Yeah, no, right? 1, 2, 3, dot gets parsed as the number. And it gets parsed as 1, 2, 3, followed by a dot, followed by the literal 4, 5, 6. Which I think is what we expected. So a number is only allowed to contain a single dot. But there's still something wrong in the sense that if the parsing fails, it still gives us something weird. So how can I make it fail? Because I guess actually there's another argument here, which is I think a number that matches this cannot possibly fail to parse. But let's say we just like allowed underscore in here, right? Then what I really want is for this to give us a nice error message. And I'm curious about why it doesn't. Because the alternative, right, is we remove this case and then we just .expect on this saying, we know that literals like this must parse correctly. But why does it give me an unhelpful error? Oh, it's because I haven't added with source code. How about now? How about now? Yeah, this numeric literal. But why does the invalid float literal? Okay, great. So the parser doesn't, the actual parse of floating point numbers in Rust itself doesn't give us a very good error. But now we can take that away. So you said, if I do .456, what should that parse as? .456. I think this is correct. I don't think implicit 0 is a thing that LOX lets you get away with. But it's an interesting question. Like if I go to numbers, .456 should parse as dot followed by 456. Yep. So we parse that correctly. It must start with a number. Okay, so I think we now have the parsing of numbers. We have the parsing of all of the like double character things. We don't have idents and strings yet. These are actually pretty... I'm going to do idents because idents are pretty straightforward. Idents are really just numbers where you don't need to parse anything. So let's do like 31. So we're just going to copy the stuff from this. First non-ident is going to be anything that doesn't match what, A to Z, A to Z, A to Z, or A to Z, or 0 to 9, or underscore. Also, I mistyped there. Right? Is there anything else that we should allow in identifiers? Nope. Go back. Identifiers. Those are all fine. Those are all the characters we allow anyway. First non-ident. And so now we don't need to do any of this dot checking. We already checked that it starts with a letter, not a number, a letter or underscore. So that part is fine, which means we can do this. First non-ident. Doesn't need to be mutable. We don't need to do this extra dance. We need extra bytes. We don't need to do any parsing. And we can just say ident. So that one's pretty straightforward. But now there's an interesting part, which is let kind is we're going to match on the literal. And then we're going to have to extract out these. Because these ones are special. And I don't know whether they're supposed to be case insensitive. The language doesn't really say. I'm going to guess that they're case sensitive. So I think we're just going to do token kind and. Oh, this is going to be. Okay. Let's make this a little bit smarter and save ourselves some time. QA. Okay, let me, for once, actually talk through what a Vim macro is like. So in order to do a Vim macro, what you do is you first click Q, and then you give a name to the macro, which is a single key. So A. So QA. I'm now recording a macro named A. You see this in the bottom left. Then you can write you can just do any Vim commands that you want, and they get recorded until you can hit Q again. So in this case, what I want to do is I want to copy the next word. So YW, you can see this in the bottom right, YW. Then I want to add a double quote and another double quote and an arrow and token kind : and then escape to get out of insert mode. And then back to the start of the line. So that's caret. And then P to paste in, and then back to the start of the line, and then one to the right, so L, and then I want to make the word lowercase. So that's GUW for make lowercase the next word. And then because I'm going to execute this again on the next line, I want it to automatically progress to the next line for me as well. So I go one line down with J, I go to the start of the line, and I hit Q. So now I've recorded that sequence of events. And notice I didn't type and anywhere because I was copying the previous, the word that was already there. And so now I can hit ampersand A to run the same thing again. And then I can hit ampersand to run the same thing again. And in this case, I can run, 10 ampersand, and then it will do it 10 times. And so eventually now it's done the thing that I wanted. And so for anything else, I just wanted to return ident. And then the actual kind here is going to be kind. Sorry, not ampersand, at. The at symbol. That's a missaying of mine. What about 1, 2, 3 dot? What should that be parsed as? I don't know. Let's see. Numbers. 1, 2, 3 dot should be parsed as 1, 2, 3 dot. That's really interesting. Okay, so let's add that in. That should be pretty easy for us. So that does mean that this needs to go back to a match. Because now we have this case, which should do this. And we have leave literal as is. And then we have the to case if 2 is empty. Then the literal should just be 1. So let's see. So if I now did a 1, 2, 3 dot, it now gets parses 1, 2, 3 dot. This also feels like a thing where we should really just add a bunch of unit tests, right? Doing so should be pretty straightforward to this. But I'm going to not do it because I'm contrarian today. So if I now write here and, it gets parses and. And if I write and f, it gets parses identifier and f. Beautiful. Okay. No, 1, 2, 3 dot is apparently supposed to be 1, 2, 3 followed by a dot. As you can see, this line is parsed into this. So our old implementation was wrong. Okay, and then I'm just not going to handle strings yet because strings are hard and I don't want to deal with them. We're going to have to deal with them pretty soon anyway, but I think now we've gotten pretty far. Okay. So, git add dot, git commit most of the tokenization. Git push. See what happens. Wait, it skipped step 18. Step 14, 15, 16, 17 complete, and step 19. And now step 18. Okay, great. Thanks, step 18. It built successfully. What does that mean? Oh, it's compiling again. Okay, we failed. We failed the first test case because end of file is supposed to be end of file space space. Wow. Go back to the drawing board. Back to the drawing board, everyone. We messed it up. It's completely wrong. Major regression. Fixed. Try that again. All test pass for empty file. Okay, great. Let's see what happens. Like how many steps do we think we succeed at now? Okay, so we got empty file, parentheses. Okay. Can I just mark stages complete? Wait, did it test my thing? Test failed. Expected line 1 on standard out to be left brace, got left brace double space. So there's a line here somewhere. Is there an extra space? Oh yeah, I do have an extra space. Full of bugs. No. Full of bugs no more. This was the last bug. All test all seems like a lie here. Okay, test passed. Great. So now it agrees that I passed that one. What about braces? Test pass. Okay, but why doesn't it mark it as complete then? I guess I'm supposed to read it. Mark stage is complete. Other single characters. Running tests. Hey, test pass. Great, mark stage is complete. Lexical errors. Wait, no, lexical errors. A series of tests that contain unknown tokens mixed in. Errors should be printed to the standard error stream starting with the line N prefix. And you must exit with exit code 65. And it has to match that format. That makes me so sad. That makes me so sad. So luckily we can actually do this with Miette too. It just makes me sad is all. Which is we're gonna need a structured error type. So we're gonna do this with so up here. We're going to do a pub. Should it be a struct for Miette? I forget. Yeah, I think it's a struct my error type, which is we're just going to call error. It's not going to be a Miette error. And then we're going to derive cargo add this error. And then we're just going to bring in this entire thing down here. And with all of these. It's not going to have a code. Not going to have an error. Oh. Tokenizing failed. So the source code, the label, if we want to have multiple labels, but see, oh, and I think all of these can then be turned into, okay, this might actually be okay. This might be okay. This might be okay. I think all of these error types can then be turned into Miette errors, and then we can downcast it in the outer thing to make sure we give the right thing. That's real stupid, but okay. So this is actually not going to be error. This is going to be like single token error, which is silly, but you know, unrecognized token, token, which is a character. And then we don't need any of the other labels. And then now this is still going to be a Miette errors. And then down here, so this is still going to be a Miette error. But what we're going to do here is, this is an example of a token missed. And so what we're actually going to return here is a single token error where the source is going to be self.whole.toString, where, and in fact, maybe the error now can capture the lifetime, but lifetimes in errors are a pain. So we're not going to do that. The token is going to be C. The error span is going to be this. And then I guess actually we can even do this over here. So the real error we want to print here is this, right? Unexpected token C in input, where this is token. And so now down here, what we actually return is this, but dot into. this should be a source span, and we've made it a labeled span. This character. This input character. So this is now a source span instead, which is fine. Source span, like so. What? Source span. New. Doesn't like that, does it? Okay, how am I supposed to use this? Why can't it just be like the other one? From range. Okay, great. So I can do from. Great. See, so now we're just returning a concrete error type here instead. And then we can do the same thing for the numeric parsing if we really want to, but we also don't have to. Like here, remember, we can because they're all bubbled up as Miette errors, we can combine opaque error types and actual error types. And so where this now gets interesting is up here, I can do match token. So if it's okay, then that's easy. The token is the token. Otherwise, if it's an error, then if let some unrecognized is e.downcast ref to single token error. So if we can turn it into a single token error, then we can std process exit with, what did they say we had to exit with? 65. Okay. So then we will return, if it's not one of those, then we just return the error, we print it nicely, etc. If it is, then what we'll do is we'll ePrint line the full error, and then we will print on standard out a std error. No, that's fine. So we'll just on std error print this as well. Then ePrint line this, where the character is going to be unrecognized.token. And then we also need to find a way to get the line out of this. So impl single token error, pub fn line. And getting the line is real annoying, actually, because it's going to be self.source. Until self.errorspan.offset. So we're going to slice the string, which is everything from the start of the string until the start of the thing that we are highlighting as being unrecognized. And then we're going to count the number of new lines. Right? So this until unrecognized is that. Oh, source span has a line error. Oh, error span. Does it? I think you're lying. I mean, that would be amazing if it did, but I don't know if you're right. Oh, it's a trait. That's great. So then it'll, I mean, if that's the case, then self.errorspan.line, were you saying this I can get through a trait of some kind? Span contents line. Span contents. No, something's wrong. source code. Ah, it's specifically on source code. So what is it implemented for? It's implemented for Miette span contents. No, that's not quite right, because it requires that I already have one of those, which I don't. I think this is something it uses internally. So I'm gonna stick with my version. So because it's like not really that bad. It's until recognized dot lines dot count. Right? And I think that's right. It might actually be up to and including. And then it's the number of lines. So imagine it's on the first line. Then the number of lines in there, I believe, would return. I mean, this is an easy thing to test out on the playground, right? If I do main and I do print line of whatever, and I want ABC dot lines dot count 1. Yeah, so it would return line number 1, which is what we would expect. So this is then going to be line N, where that is going to be unrecognized dot line. And so if I now do, what's a token that doesn't exist? Pound. Yeah, so it prints now line 1, unexpected character, pound. And then if I add some new lines, then now line 3. Great. Give Codecrafters what it wants for errors. And so notice we still now have all the Miette niceties, but we just can also downcast to conform to what the sort of testing suite here expects. You can't exit immediately. You need to print all errors. Really? But you can't safely tokenize after you hit an unknown token, right? Because once you hit an unknown token, you don't know whether that token should have been multiple characters or 1. So at that point, you might be sort of desynchronized from the input stream. So I'm like, it might be the LOX does something different, but it's not obvious to me that it should continue parsing. I guess maybe this is like a recover as best as you can kind of thing. I see. So it still expects to get end of file. Okay. Well, if we want to be forgiving here, then what we will do is, I mean, it's easy enough to do. We just print all errors, and if any CC error is true, and then at the end we say if any CC error, then process exit 65. And then we also need to continue, which I think is fine. There's an interesting question of what our parser does in that case, but I think, so what this requires is that if you fail to parse, your parser is in a state where calling it again won't just produce the same error, which luckily for us is the case, right? Because we move past C before we return the error about C. So I think that should be okay. And I guess we could try it with something like pound, bang, bang equals. Yeah, so we get line 1, unexpected character, pound, bang, and a bang equal, and then into file. And the output of that is 65, which, just so that I double checked, should be 65, right? Yes. Contains one line for each valid token, even if other lexical errors are present. I guess it said right there, and I just didn't read it. This output format matches the spec in the book's repository. You're free to print errors first, last, whatever. Okay, that's fine. Only lines to start with that. Great. Okay. Keep going after errors. All right. Mark state is complete. Hey, assignment inequality. Yeah, we already dealt with that. Negation and inequality. Didn't say all test pass? Yeah, it did. Test pass, test passed, test passed. It's happy with all of them. Test passed. Here too, all test pass. Yeah, this is bangs and inequality. We've done that. Next. Oh, in the CLI. Oh, it no longer says all test passed. Nice. It's been fixed. That's really good. It says test pass. So it's like the current stages tests, really. Nice. Okay, great. Test pass. This is relational operators. Yeah, we handle those. The division operator. Oh, we need to handle comments maybe. Are those supposed to be special? That's an interesting question. Scanning punctuation. What? There's not an example for it. That's interesting. Longer lexemes. This is going to be bright. Okay, that's fine. Right, but are they considered... Oh, I see. It walks to the end of the line. Okay, so comments are special. Great. So this is started slash. That's fine. I like this pattern of started. It's turning out very nicely. So down here, if what we started was a slash, then, and here it is in fact the next character needs to also be a slash. So here we don't need to do the thing that we did for the sort of paired things like less than and equal, where we have to skip the white space in between because slash space slash is not a comment. So this one is actually just if self.rest.starts with a second slash else. And the else case here is easy because it is just some token, no, some okay token. Fill struct fields origin is the cster, kind is token kind slash. And then if the next thing is a slash, this is a comment. See the meta commentary? Isn't that great? So at this point, if it starts with a slash, then what we want to do is keep reading until we hit the end of a line. So I think the easiest way for us to do that is self.rest.lines.next dot unwrap or self dot rest. Now, what's a little bit awkward about lines is that it skips the terminator, which we need in order to correctly compute bytes. And I don't think there is a... Yeah, I mean, we could use position here. We could just like search for them ourselves, but it'd be nice to reuse lines just so we sort of get the R and N, because it's not sufficient to look for \n, because on older Mac OS devices they use just \r. So it depends on how technically we want to follow the spec here. I guess I don't actually know what the spec says for this. Whether the spec specifically says the spec specifically says \n. Interesting. But here it handles \r. But \n is the only character used to indicate new lines. And so armed with that knowledge, I think what we can indeed just do self.rest.position find, \n unwrap or else self.rest.len. And then we want to do self.byte plus equals line_n.len. And then we want self.rest is self.rest starting from line end and onwards. Line end actually we actually don't want to do that. We want self.rest. So the reason I don't want to do this is because it actually has to be line end plus 1 so that you skip over the new line. But line end plus 1 will cause the slicing to panic if we hit this case, because length plus 1 is not something you're allowed to split at to slice from. But I think split at the argument mid should be a byte offset from the start of the string. It must also be on the boundary. So it doesn't actually say. So what happens in here if I do debug, please? If I do a dot split at 1, which is the length of the string. That's fine. And if I do AB and split at 1, I get AB. Which means that in our sort of way of the world here, right? What that means is we would, if we use split at, we would include the new line. So what happens if I do A split at 1 plus 1? It panics. Oh, I guess we can let that's a good point. We can just let the new line go through because we skip white space later anyway. Yeah, you're right. So we can just do this. Unwrap or else. What am I? Oh, right. Line end here is a... and then we want to continue. right? So we look for the new line, and if there's an end of file, then we just point one past the end. We add the something's not right. Oh, self.rest includes the second slash, so we don't need a +1. But we read. So imagine there's a slash and then immediately a new line. Then find is going to return 1 because 0 is going to be the second slash. 1 is going to be the new line. And so find is going to return 1. So we're going to add 1 byte and we're going to move on 1 byte. And then we're going to start from the new line. So that's all good. And this would be the same. Okay, yeah, I think I'm convinced that it's okay. Okay. So this is skip comments. This is also where writing unit tests would let me just test this. I really should just do that, but I don't want to. Test passed. Great. Back to here. All right, let me make this dark for you all because otherwise you're all sad about it. No, solarized dark. Can I make the whole thing dark? Question mark. UI orientation. Nope. Oh, I might have to change it in my browser settings or something for it to be happy. Well, I guess it's going to stay a mix now. Division operator, test passed. I don't get the sparklies automatically anymore. That's sad. White space. White space I think we're good on. Test pass. Great. Mark stage is complete. Multi-line errors. Series of tests that contain lexical errors spanning multiple lines. For example, if test logs contains this. Oh, this is just to check that our line count is correct, right? That's fine. It is correct. Great. Mark stage is complete. String literals. String literals we haven't implemented yet. So this is the next one we're going to have to do something about. All right, string literals. Time to battle you. And this is where let's go look at what the book actually says about string literals. String literals. Now that we're comfortable with longer lexemes, I don't know if we're comfortable, but it's interesting that they handle this first. We handle it last because identifiers are easier. Lox doesn't support escape sequences. Oh, then this is super easy. Okay, great. So then it's just look for the ending double quote. For no particular reason, Lox supports multi-line strings. That's fine. For the last instance, when we create the token, we also produce the actual string value. We don't need to do that. That happens automatically for us. If Lox supported escape sequences, we'd unescape those here. Okay, well, this is great news for us because it means that our unescape here is Lox has no escaping. And so therefore, this just returns cow borrowed of S. Great, we now have unescaping. And then here in strings, all we have to do is if let sum end is self.rest.find double quote else, otherwise we can actually return a pretty good error here. Are we expected to give some like particularly good errors here for strings? Unterminated string. Right, but is this supposed to be the line number of the start of the string or the line number of the end of the string? Because LOCK supports multi-line strings. I think it's probably the start, because it can't be the end, because the end would just be the end of the file. So I'm going to assume it's the start. So that means we're going to have to downcast here to produce it the right error type, which means we can do this. This is now string termination error. And what does that unterminated string in input? The in input is not really necessary because it's always in the input. And then this is going to be string termination error. Source, and I guess the span here is just going to be the entire literal. So I don't think we even need a token. And so in this case, so in the else case here, we're going to say that source is a whole string. There's no token. And the source span is from self byte until self.whole.len, right? And it's including the starting double quote. Error appeared out of nowhere, not input. String termination error. If we do find the end, then this is also really easy, right? Because it's just self.byte plus equals, well, we read up until end plus 1. Self.rest is going to be self.rest from end plus 1. Right? And some okay token. This feels too easy. So the actual, I guess the actual literal is actually self dot, is self dot rest. So we don't want C onwards here because C onwards would include the opening double quote, which we don't really need. So it's just that until end. So the origin is literal and the kind is token kind string. And this is that onwards. Feels far too easy, right? Hello world. Oh, I see. But the I see. Okay, so technically, if we want to be really accurate about this, notice how the raw part of the file is supposed to include double quotes because it's the actual literal we parsed. Well, we have two options here. We could cheat and just print the double quotes ourselves because we know they must have been there, or we have our unescape just remove them. And I actually think that's what I want to do. So that means the literal is going to be, I can't type on this keyboard. C onwards to end plus 1 plus 1, right? So plus the C onwards plus the 1, which is the starting one, plus the 1, which is the terminating one. These stay the same because the things we're skipping over are still the same. The literal now includes the double quotes. And then our unescape, so just remove the, is just now S. We could actually here do trim matches. Since it has no escaping, can't contain, strings can't contain this, so trim won't trim multiple, right? Because otherwise the concern is, what if someone wrote a string that is like, even then trim matches wouldn't do the wrong thing, but ABC, this, right? That would be a problematic case if we use trim matches, because it would trim off both of these, not just the last one. But in this case, it's not a problem because you can't put double quotes and double quotes if you don't have escaping. So now that does the right thing. And if I tried this, it says, oh, that should not say input character. That should say the string, this string literal. And in fact, if I now do E and I do new line, this string literal. And if I do world actually banana, then it highlights that whole string literal. Although it it still now gives identifiers for all of them. That's not right. Why does it do that? Oh, okay. So this is another interesting case, right? Like when you continue on error, weird things happen. So we error when we parse the double quote, right? When we parse the double quote, we error because we don't find a closing double quote. But because we've been instructed to continue even though we hit errors, then now the question is, okay, does that mean that there are no more tokens because the string letter was never closed? Or does that mean that we now continue parsing from after the double quote that didn't terminate, right? These are the things that you run into as, I don't know what you wanted, so what do you want me to do? Yeah, like arguably this is correct, right? It continues from right after the token that it wasn't able to deduce, rather than assuming that this token actually runs the length of the file. You can see this in Rust, right? If I just put a double quote here, then now the entire rest of the file is, well, until the next double quote, is marked as a string. So this one here, it will actually eliminate the remainder of the file. It must be part of the string, and I will not parse it. Or I will not, tokenize it. So I don't know what behavior they want. I wonder if we go to strings, that's not going to be helpful, is it? Swallow the remainder of input. Swallow the remainder of input as being a string. So I think here too, we're just going to do self.byte plus equal self.rest.len. And self.rest is empty. It's fine. What? Really? Okay, fine. Self.rest. Self.rest.len. And so now if we run it, it just says end of file. Although now our error is all wrong because it tries to read self.byte. Great. So now that does the right thing. And then we need to do the downcasting again over here, which is else if string termination error, then we want this to now, what do they want to be printed? Unterminated string. Unterminated string. terminated. Like so. And that will give us the line number. And again, this is assuming that the starting double quote is the line number they want. Dot at the end? Dot at the end. But that's not required for unexpected character? What is this? Where's the lexical errors? That one does not require a dot at the end, but this one does. That's unfair. Okay. So string literals. Straight from the book. Yeah, I believe it. I mean, this is probably exactly what the book says. It's more, it's just unexpected is all. Inconsistent. See, test pass, but I don't get the automatic thing. Makes me sad. Mark stage is complete. Okay, number literals. That one I think we've already dealt with. Hopefully, correctly. Test failed. Ooh, it's exciting. Number 77. Expected number 77.0. Okay. So in other words, for numbers, the literal is expected to always have at least one decimal point, which Rust's printing of floating points numbers does not do. So here's what we'll do. If n dot no, that's not what I want. I want so I don't think there is a in the formatting of Rust. So let's look at format, I guess. I think that's going to rewrite me to here. Oh, maybe I was wrong. Yeah, no, I was right. Precision. An integer name followed by a $sign. Use format argument as a precision. For non-numeric types, for integral types, from how many digits? Yeah, so the problem with using this is that it's a maximum. It's print this number of decimals. It is not print at least this number of decimals. Right? So I actually think that won't work. In other words, if I here do print line dot 1 of 1, it'll do the right thing. What? Oh, it's what did I do? Why are you not running my thing? Okay. One. Run. Oh, Lord, why? Well, this will print 1.0, which is what you wanted. However, it won't do the right thing because if I do 1.532, then this will actually just print 1.5 because I've told it use a single digit. In fact, I can prove it to you. This will print 1.5 because I've said precision is exactly 1. And so that will not do. So I think we actually do need to do something like if n, I think there actually is a, fract not equal to 0. Or rather equal to 0. Then this. Tests require that integers are printed as x.0. Oh, there's also trunc, right? The integer part of self. Okay, so if n is equal to n.trunc is nicer. You can do... Oh, you can do the debug print? Really? Skeptical. Why has the playground forsaken me? Oh! What did I do? I have no idea what I just did. Oh yeah, the debug print does do the right thing. Although, I'm worried. Yeah, see? This is what you get when you do debug print. Ain't okay. It needs to print this. So debug print is not okay. Debug print prints scientific notation. Integers with .0. Great. Okay. Boom. Identifiers. I think we did identifiers. Yeah, mark stage as complete. Boom. View next stage. Okay, reserved words. Oh, there was one more. We failed the tests. Print. I knew there was going to be one we missed. I just knew it. All right. Print, and then I really want these to be sorted. I guess they were sorted, and I'm just print down here. Print. Parse print. Whee! Mark stage. Okay, great. We're now at parsing. Now we're starting to talk here. So this is the first under parsing expressions. Can I like hide this top one? I guess maybe not. In the stage, you'll have support for scanning reserved words. No, that's the one we just did here. In this stage, you'll implement support for the parse function. Hey, make sure you've read representing code. The code covered in that chapter will be required to generate the output tested in the stage. Recursive descent parsing. So this is where we're not going to follow the instructions and we're going to do our own thing instead and implement a Pratt parser. Okay. However, first what I will do is mod lex, and then I will do all of this stuff. Great. We'll go in there. Pub mod lex and pub use lex lexer. Main. So this is going to be here lex. Okay. And then we'll do the same here. Parse, parser. Parse. Okay, parse, create module, go in there, lex, and then we will do, we have tokens, that's all fine. And now we're going to have to do pub struct parser. Don't know what goes in there yet. What am I doing? Parser, pubfn new. And this one is going to be surprisingly similar in the original setup here, I think. I think we'll still make this generic over the input. And it's also going to have a lexer. Like so. Import that. And so now the interesting thing is going to be, I guess we don't actually want a new parser. Oh, maybe we do. I was going to say we could just have parser do the parsing directly, but I think it's nice to be able to create new before you do the parsing, because that way you could like configure options, debug, print it, whatever. So we're going to do parse. And it's going to consume self probably. And it is going to return a result of an AST, which we haven't defined yet, and a MET error rather. Okay, and we're going to have a pub struct AST. Now, for the parser, this is where it's very helpful if you've already read the Matplotlib article. If you haven't, this code is going to look a little bit mysterious. I'm not going to talk entirely through why it works, because I think the article is just so good and it's worth reading. But what I'm actually going to do here is go to the article, scroll all the way to the bottom, grab this guy, copy, and throw this in here, just so we have a reasonable starting point. Now, we already have a lexer, so we don't actually need that part. Now, we do probably... Right. So there is one thing we're going to need, which is, I think actually this is not going to be a lexer. This is going to be a std_iter peekable lexer. And you'll see why a little bit later. And then parse down here is going to do I think we can actually move all of this into I'll explain some of this soon. Min_bp. Just give me a second. So this is actually going to be mute self, parse within 0. And then down here, that can go away. This can go away. And then 60 parse within. I promise I will explain it. I'm just moving code around at the moment. Okay. And this is actually going to be, I guess, self.lexer.next. Left-hand side is self.lexer.next. Just transforming the code to match here. Self.lexer. Nope. Self.parse within. Self.parse within. It'll be easier to talk through once the names sort of the names match here. So flexor peak match op.kind. And this is going to end of file. It's just none. This is some. Actually, this is token where the kind is token kind op. A lot of this will not actually make sense yet, but I promise I will explain once I can. Actually, yeah, I'm gonna give an overview of the Pratt parser. I'm just sort of trying to translate the method calls and such so that I don't have the screen full of errors. Makes it a little bit easier to explain what's going on. Match op. Right, these need to be pub. Suppose. What? Oh, right. This is going to be a little bit annoying, actually. I'm just trying to get the code in a place where it's easier to explain without all of the errors. But I may just have to write it top to bottom for that to make sense. Which is a little bit annoying, TBH. But okay. Let's do that. Okay, so parsers. At a high level, what a parser does is it takes a sequence of tokens, like the things we've already now scanned out of the file, and it... Wait, let me just open a window. It's too hot in here. There we go, that's better. Ooh, air. It takes a sequence of tokens like the ones we've just written Elixir for, and then it tries to put them together into an abstract syntax tree. So it knows about things like operators that have operands, like which side binds more tightly. Basically, how do you take this like random sequence of tokens and turn them into a program that actually has structured? Like things are inside other things. Things like parentheses actually indicate a group where the things inside are logically sort of children of the group. That kind of stuff. That's sort of what you're aiming for with a. That's what you're aiming for with a. Parser. The word escaped me. Now, when you're writing parsers, there are a bunch of different ways to write them. And a recursive descent parser is one way which you can write them, where you sort of start with, I'm going to butcher this explanation, but with a recursive descent parser, you... you have recursive, in fact, I think there's a good example in the article. Let me pull that up. So if you go near the top here, right? So this is parsing, very visually explained, right? You go from a string that you've turned into tokens, like here, 1 is a token, plus is a token, 2 is a token, star is a token, and 3 is a token. And you turn it into a tree that represents how those operations are combined. And you'll see here, for example, the multiplication has sort of stronger binding power than addition does. And therefore, the multiplication happens together, and then the addition happens over the result of the multiplication. And this is a sort of grammar, the way that you often express how a language should be parsed. And down here, you have this thing called recursive descents, which is a fairly simple technique for parsers is often the one that people start with. And the idea is that you write a bunch of functions, and those functions call other functions which call each other, and there's they recurse into each other as they encounter a thing that should be parsed. So this being an example, right? If you know that the next thing you're supposed to see is an item, you call the item parser. The item parser looks for the next token. If the next thing is a struct, then it parses what follows as a struct. And so it calls the struct parser. And the struct parser, in turn, expects that the first thing out of this should really be lexer. The next thing out of it is the struct keyword, and then it expects there to be a name, so it calls the name parser. And then it expects there to be a curly bracket. And then it calls a field list parser, which parses the field list. And you could imagine, for example, that if this wasn't struct item, but maybe it's mod item, then mod item in turn might say, oh, I've encountered a new item in here because I expect the children of a mod to be items. So the mod item parser might actually call the item parser to parse the individual things in there. And so it recursively descends into the file that you're parsing. Now, where this gets a little bit awkward is left recursive grammars. So the idea here is that imagine you have a so here is a good example. So a sum is a if you want to allow like multiple pluses, then what becomes weird is if you have, let's say, 1 + 2 + 3, because you have to parse it as 1 + 2 + 3. But when you start, what do you parse it as? Because your definition of what a sum looks like is that it might be an int or it might be a sum plus int. When you stand at the first integer, you don't know whether this is an int and then there's just something else after that you're not supposed to parse because it's supposed to be handled by whatever parser called you, or whether you should read and try to parse it as a sum. So either you need some way to like backtrack your parsing to say you try to parse it as a sum that might have a plus in it. And if you succeed at that, great. If you don't succeed at it, undo the steps you just did and parse from where you were when you were standing at the integer instead. Because again, all of these parsers are expected to only consume what they are supposed to parse. If the name parser here tried to like parse the rest of the input, then it wouldn't work because the rest of the input is not a valid name. So it needs to parse the next token only, which for name is easy because it's just the next token. But for something like an item, it's tricky because you're consuming lots of tokens that make up the struct, right? So each parser only needs to consume the minimal amount, the minimal number of tokens that make up the thing it's supposed to parse, and not leave all of the rest for whatever parser is called next. But in this sum case, it's really hard to do that because you don't know how much you're supposed to consume. Are you supposed to only consume the integer you see immediately? Or are you supposed to like consume and look for a plus and then consume some more? Because if you go this path, you might fail and then have to like go back and try the other parser instead. And that's possible, but really complicated. You can, for at least handwritten parsers, as it says here, you can like combine recursive descent with loops. So you parse an int and then you try to eat pluses and integers as long as you can. So it is possible, but you end up with a lot of these weird corner cases where you have to like manually write them a lot. And for every operator, the parser becomes sort of specialized. Pratt parsers is a way to construct your parser so that it just handles arbitrary expressions, and there's a very easy way to express how to group things. And again, read the whole article for the details. I highly recommend it, but you'll see how the sort of structure of this ends up being pretty nice. So the first thing we do when we start parsing is we need to look at whatever the first token is, right? Like we don't have an option. We're a parser and there's a token right in front of us. We need to look at what it is. So the first thing we do is we consume the next token. And depending on what that next token is, we need to figure out, okay, what do we do now? Well, if the next thing that we see is an atom, like a literal, then the thing we should return is a literal, because literals don't have arguments. There's nothing to group them with, if you will. They are, as we might say, atoms. Now, our tokenizer does not actually produce atoms. It doesn't tell us that, a parenthesis is, not an atom, but a string is. So instead, what we're going to have to do here is something like if we hit a sum, and this, we're going to have to transpose question mark here to propagate the error. Wrap error. Unexpected end of file. So depending on here, nope, match. So, I guess I can do S here. That's fine. See, this is where I really didn't want all these errors. It'll be okay. Actually, maybe I can do this to make it slightly less noisy. Just trying to make it as unnoisy as I can. Miet. I need mieps wrap error. Great. That is now much less noisy. And then down here, we can just return like a okay of this. And now actually, I think I can parse within. I think I can get this even less noisy with this. And then we can look further up. Great. Now this is looking much more reasonable. Yeah. All right. So when we look at the very first token that we get, we first need to decide, is this a thing that we're just like, this level of the parser, if you will, is done. Like, for example, if we hit a string literal, we're done. We can just hand that up the stack as like, this is an atom. There's no operation involved here. And so if you look down here at atom, in this particular language that Matcloud was using, atoms were always characters. So it would be things like, you can see the example here of all of the tests are like, F plus G, or they're literals as in numbers, but they're always just single character. In our case, of course, that's slightly more complicated. So here, for us, that's really going to be a token. And in fact, it's only a subset of the tokens. It's only things like strings, numbers, booleans. And in fact, I think this is basically what the exercise is, right? Well, in this case, it's just true, false, and nil, which actually, we don't parse nil. This feels like a thing that should have been tested, but isn't. Right? Isn't nil special? Oh, we do parse nil. Okay, great. So there's only a subset of the token kinds this can be, but we're just going to leave it like this for now. And then cons here is really just saying it's an operator applied to a set of operands. And it doesn't really say what that operator is. In our case, we can actually say this is a token kind, but it's not really a token kind. It is a type of operator. So we could be a little more explicit here in the parser and say that enum atoms. So our atoms are string, which is going to be a dster. They're going to be numbers, which is going to be an F64. They're going to be nil, and they're going to be Boolean. Those are all our atom types. And I guess instead of atoms, it should just be atom. And our operators are, if we go back to look at our lexer, the operators we have are these. Not semicolon. So we have minus, plus, stars in multiplication, bang equals, equal, less equal, greater, less, greater, slash for division, bang for negation, equal for assignment. These are atoms. And is an operator. And so is if. Else is not, actually. So if is an operator that takes three operands. The three operands of if are the condition, the yes branch, and the no branch, or the true branch and the false branch. Now, I don't know if this is the way that the book parses this, but like, it doesn't really matter. We're just constructing the syntax tree, and then we can always print it out in whatever representation we want. The reason the enum is called S is just that's what it was in Matclads. We can rename that pretty easily. So if is an operator, for is an operator. Fun and class are not operators, they are groups. So we have groups, and groups are things like a class, and groups in turn contain S. Right? So a group is going to contain, these are the, and maybe if we give S a better name here, we can rename S to token tree, right? That's what Rust ends up using for this. So a group can be a class definition. And in fact, we could also not parse out things like classes here. We could instead parse them out as it is either a delimited group that has a delimiter, which is let's say a character delimiter, and a block. And in fact, maybe this is just all it is. Maybe a group is it might have a name. It has a delimiter. So the delimiter is the opening and closing bracket. And so actually we could have enum delimiter. So that can be curly, which I guess is brace, right? It's paren and brace. So there's a delimiter. And so that actually means that if you think about it, a for is sort of also a group, but it has to be special, I think, because I think it has to be considered an operator, which makes it interesting. Maybe class is just an operator too. I think it is. I don't think we need this group concept. I think a class is just an operator where its first operand is the block that defines the class. This is essentially Lisp, right? Like this is what Lisp tries to tell everyone, that everything is just S expressions. And so I think now we're basically agreeing with them that yes, it is. So op, which means a function is also just an operator, right? So a function is something that takes a few operands, the operands being the name, the parameter list, and the body of the function. If we already talked about, print is an operator. Return is not. No, return is. Yeah, I'd have to think about this a little bit because return, I suppose, is an operator in that its operand is the thing to return. Oh, did I not put or here already? Oh, you're right, or. So return is an operand, an operator. Print is an operator. Super and this. So super and this are just identifiers, I think. And so I actually think up here where we have atoms, I think the last atom is ident. And I think actually an ident is a... an ident here is just a string. But I think here, one operator would be like a field. So a field access. So a dot b is not one identifier that is a dot b. It is a field access where the two operands are a and b. So field access is going to be that. So super and this are both going to be identifiers. And I guess we could have that be in here as super and this being distinct from just arbitrary idents. Var is definitely an operation, and while is an operation. Great. And we can fill the rest of that out in a second. So when we now go back up to here, we now need to look at, okay, what is the next token? Well, we could handle the then we actually want to hear, this is not unexpected end of file. This is it's like bad token. Expected expression, I suppose, or something. We could come up with a better information about what layer we're at here, right? Because parse within is going to recursively call itself. So we really want to give more context here about what were we looking for. So we could actually say here in the sort of call stack, looking for is op and usize. So which argument of what operator are we looking for? And I guess the root of the program isn't really looking for anything. So this is an option. This is, again, just in the interest of giving better error messages. So we could say here, wrap error with, if let's up and arg_i is looking for, then argument for op. For now, at least, we can always make that better. And then here we can derive debug, clone, and copy. We can do the same thing for op. And we can even do partial eq for this. We can do the same for this. Do the same for this and this. We cannot do copy for that. Just clone. Okay, so argument number arg_i for op. And if we don't know what we're looking for, then that means we must be looking for a statement, I suppose. Because like the top level of a program in some sense is an operator too, and it is a sequence of statements. Right? So actually this one's a little weird because in some sense, in some sense we want to keep parsing, and then every time we should expect to get a full statement until we get a semicolon. All right, we'll get to that in a second. That's fine. So out of the things that we might get here, I want to also handle the option case. So for the option case, we want to say unexpected end of file. And we can even do looking for is this. Like this. Okay, or else. So here what we're doing is the transpose here might look a little weird, but we try to grab the next token out of the lexer. Transpose means that we turn option result into result option. So we get the result first. And then we wrap the error with information about what we were looking for to give slightly more information to the caller about sort of the parse stack we've gone down here. Because remember, this is recursive descent, so we're walking down some structure. And so it'd be nice if it said like, while looking for the first argument of this, while looking for the third argument of this, etc. And then we question mark to get out of the result. So now we're left with an option token. If the token is none, that means we got an end of file. If we got an end of file, then we want to, I guess actually, we probably want this here. Because if the if we hit end of file, I feel like we want to treat that specially, but maybe we can just do, maybe this is actually the argument for having a pub struct end of file, that we can go over to lib, and no, over to lex and grab our, this thing for it, unexpected end of file. And the reason I want it to be its own type is so that we could downcast for it. So now here we can do end of file. Which really can just be okay or this. Because now up here, we can do match on this. And if it's an okay TT, then we return okay TT. But if it's an error E, then I suppose if E downcast ref. So if we can downcast that to an end of file, then, oh, I guess we could have a sequence operator. It's something the language doesn't really have. So the advantage of not having an error enum is that we can actually use the miet wrap errors, for example, and just have it all produce the same type, which is pretty nice. This feels bad. I suppose one option here is to just represent this with nil. Right? So we actually just do like end of file is not actually an error here really. Okay, I think I want this to not be such a mess. We're gonna just match on this. And if it is okay of sum of token, then we're gonna give back token. If it is okay of none, then we're gonna give back okay of token tree of atom of nil. Feels like cheating, but and if we get an error E, then we want to return. Oh wait, it's the other way around, right? Okay of this. So it's a sum of okay. It's a none, and it's a sum of error. Then we want to return error E, wrap error. Whoa, what did I just do? There. So sum error E, then we do this, and then we wrap error with that message instead of all this garbage right there. And then looking for goes away, and then this just becomes match on the left-hand side. Much nicer. Because now here we can do what I actually wanted to do, which is we can match on the left-hand side. And we can say we want to match on token. And if the kind is token kind string, just as an example, right? If it's string, then what we actually want to do is then we want to return token tree atom of atom string. And this is origin. So of token unescape origin. And I think this now can just be, we can get rid of the cow here because we know we're not doing that. I suppose we can leave it in case we ever wanted to add it later. And that's just going to require that the string here is also a cow de stir. And now it's no longer copy, which is fine. Like so. So up here now, if we find a string, then we turn it into a token tree atom. So this here you can see we're translating from tokens, which are sort of dumb, they don't know their context, and token trees, which are parsed outputs that have a meaning. Meaning this is an atom, it is a well-defined primitive in the language. And we can do that a bunch of times. So kind number, which has an n, then we don't need the origin. Then that is an atom number, where the value of that number is n. If we get a true, we also don't care about the rest. Then we know that this is a bool of true. If we get a false, we know that this is a bool of false. Like if with a keyword false. If we get a and in fact, if we get a we'll do parentheses first because they're a little bit interesting. Um, so parentheses. In fact, arguably I should do parentheses second, but that's fine. So if we get a left paren or we get a token kind left brace, then those are actually pretty straightforward to parse in the sort of Pratt parser setup, because what you can do is you can just recursively call the parser and say, keep parsing at this level. So never go further up. Like if you, this is hard to explain if you haven't read the article, but basically the argument to parse within here is essentially the min BP here is you should return rather than consume more items if you hit an operator that binds less strongly than this. And so for parentheses bind like the least strongly, or the most strongly rather. So you should keep reading until you hit a close parentheses, which is basically just keep reading until you hit a close parentheses is the only other thing at that level. So in this case, what we can say is we're looking for I guess it is the looking for that we were passed in, if you're looking for brackets. BP is binding power here, yeah. Expect. So really this shouldn't be an expect, this should be something else, but we want that dot kind to be token kind paren, right paren. Terminator is match left hand side the kind. Terminator is this. Then if it is token kind left paren, then it should be token kind right paren. And if it is left brace, it should be right brace. Then this should be Terminator. And anything else is unreachable by the match arm, by the outer match arm pattern. Yeah, so this is basically calling the parser recursively, and you'll see when it terminates early down here. We'll get to that. Actually, maybe we should go to that next before we start implementing this bit. But then let's do an operator as well so you see what that looks like. So let's say here we do, we run into a and, for example. Then, then we call this prefix binding power. This is not a prefix operator. That's not what I want. I grabbed the wrong thing. Where's my original? Something's not right. Oh, right. So this actually is kind of, I see. So this, sorry, let me get my thoughts in order. This function is a thing that parses a complete expression. And so the call to parse within here parses one expression. So it expects to get either something that's an atom or something that is a group, or something that is a prefix operator. So something like bang. But any other token represents something that is something that should have been parsed one level up. Because what we're parsing here is just the left-hand side, right? So again, we're not expecting something like and to be the left-hand side of an expression, right? We're going to look for a left-hand side and then look for an operator and then look for a right-hand side. And so the left-hand side must be either an atom or it must be a group, right? A group is fine to be the left-hand side of an expression. Or it must be a prefix expression like exclamation mark Boolean, for example, because that one is a prefix expression is something that comes before its operands. So here we can even leave a prefix expressions. And this is atoms. And this is groups. So for bang, we can pass in here op bang. And prefix binding power, we'll see in a second what does. But I guess we could do op here, match op. And there are two operators that we're willing to have come here. And it is op bang. And it is op minus. Those are the only prefix operators that we have. So I won't talk about what number this returns yet, but just notice that it has I'll talk a little bit about it. So this prefix binding power and also the other infix binding power that we'll see down here, and also the postfix binding power, all of them return two numbers. The numbers are how strongly this operator holds to its left side and holds to its right side. Now, in the case of a prefix operator, it doesn't bind to its left side at all. So it just returns unit as its first argument. Then it tightly it binds to its right-hand side with some number, which is what we return. I suppose you're right that print is, in fact, arguably, it's an interesting question what a function call is. I think you're right that a print is. Because a print in our setup here, oops. And in fact, I think actually a function call is as well. So actually, identifiers are fine here too. We actually want to cover identifiers as atoms. It's a good question. No, it's a very good question whether a function call is a prefix or a postfix. I would say it's a prefix because the ident comes first. So I think what we're going to do here is this is an ident with origin, which is easy enough. And there's actually, this reminds me that down in op, yeah, it just makes the op a little bit interesting, right? Because it means that if the Yeah, disambiguating here is interesting because sometimes an ident is an atom. I think this comes at evaluation time. Maybe. Sometimes, because I guess maybe the thing to say is that maybe an ident is always a prefix op, but it sometimes has no arguments. So essentially, the way you treat this is all idents are functions. Like everything is a function call. Some of them have no arguments. And that just happens to be how you reference a variable. Yeah, so I'm actually wondering if... Oh, yeah, you're right. Like everything is a function call because you could have a parenthesized expression followed by a parenthesized expression, and that's now a function call too. I'm gonna ignore function calls for now. That's what I'm declaring. But there are a couple of other interesting ones because a function declaration is I think is just a standard. Well, the problem is it's not an infix operator. Right, the challenge of the thing you need to parse out is if you have something like a dot b 42, then you parse this as a group, which means you're parsing that as the left-hand side. But you don't know at that point that you should expect a right-hand side because there's no operator to find. I think what that actually just means is that I do think it needs to be handled specially here somehow, and I'm not entirely sure how to handle it because in S expressions this is very straightforward, right? It's like it's a call of a field of a b of 42. So that's what we wanted to parse into. The challenge is that there's nothing in the tokenization that really tells us that this is a call, except the fact that it's something where the right hand side is a parenthesized expression. And so I guess, okay, so that could mean that it is as someone has been suggesting in chat, is that it might be that this is actually a postfix operator where parenthesis is the operator. Yeah. Interesting. I think you're totally right. I think it means that call is a postfix operator. Okay, let's try that. Let's see how this falls out. So prefix expressions are bang and print. Whoops. Print. And really, we could make this a little bit nicer by just combining them and say this is token kind print, and then we say let op is match left hand side the kind. And if that is token kind bang, then we have op bang, and token kind print is op print. And anything else is the same as there. And so now this is, ooh, what did I do? This is now op, and this guy can go away. Oh, you're right, n minus. Token kind minus. And so we got to go down here, and it's also print. Okay. So atoms, I think we covered all our atoms. Let's see if there's any others. Don't think so. I think those are all our atoms. Comments are stripped entirely during lexing. Groups are left paren and left brace. Prefix expressions are bang, print, and minus. And then I suppose this now can be op. And we're looking for the 0th argument. Of the prefix operator. And I got those wrong way around. RPP. Okay. So we've now grabbed out the left-hand side of the expression. And I suppose this thing we should tidy up, which is if we parse out the expression, we get something back. And I suppose actually this needs to... Whoa. So after we parse out the left-hand side, the contents of the bracketed group, then we should expect to find the terminator. We should expect to find, not from the movie, but we should expect to find either a closing parentheses or a closing brace. So the question becomes, what happens if the next thing is the wrong kind of closing thing? And so here, I think actually instead of an assert, I want to match on lexer.next. Because if it is none, then I want to miat bail, saying something like, this is, I suppose, an unexpected end of file. And I do actually think maybe I want to keep this guy. Let, so that this can be looking for. Oh, I suppose looking for message maybe so that we still have access to the original. And this could be move because op is copy. This is going to pass in none. And then down here, what we want is return an error of unexpected end of file. There's no really other annotations for us to add, but we do want to add looking for message here so that we also include, we got an unexpected end of file while looking for whatever that might be. And I suppose actually Yeah, in bracketed group, in bracketed expression. Did I create an init file type? I suppose I did. I think you are right. Yes. So init file, much better. In the sum case, so we get an X token, and if the token, I guess I can flatten this. If the token is equal to the terminator, then all is good. If otherwise, things are not good, because what we got is an unexpected terminator after a bracketed expression. So here, I think we return this, but here we do use miet. And I think what we actually produce here, and this is where we sort of go back to the lexer for the errors we produced there, because we're going to do something very similar. We're going to produce a custom error here, which is going to be this. Although I did something weird. There we go. And then I have a missing something somewhere. No, I don't think I do. Where is my missing closing bracket? I have too many closing brackets here. This is my problem. Right, so here what we want to point out is that in the entire code that we got, does the token give us in our lexer? If we get a token, I think we actually want not just the origin string, we also want the offset. So this is the byte offset that the operator was placed at. This should be pretty easy because it's just offset is at, right? Offset is not at, offset is, but it should be. Let c at is self.byte. And so now and I guess we could just c at is fine. Oops. C at, so that every token actually says where it came from. So that even if it's not an error at the lexing stage, we can still use it to produce a helpful error message at the parsing stage. Offset is c at. Offset c at. And it's easy because all of these, the offset is where the c was always. Because that is always the start of the token. There's not a unary plus inlocks, as far as I could tell. Okay, so up here now, we should be able to say token offset to token.offset plus token.origin.len here. So we should be able to here say unexpected bracketed expression terminator. And we can even do, I think it's hint in miet. So hint is equal to expected hop. Or is it suggestion, maybe? Ah, what is it? It is help. I'm pretty sure it's help. No? Yet. It is help. Okay. Oh, this should say Terminator. Right, because it can be an error as well. So this is an okay. But then there's also the summer error case. Which is then this. Why am I using Miette over anyhow and air? So anyhow is so generally these days I think air is slightly more featureful than anyhow is. Anyhow is totally fine still. There's no reason not to use it really, but if you want slightly more functionality, air tends to have that. The reason I'm using Miette is because Miette is particularly good at giving parser errors, because you can annotate your output errors with like source code and highlighting in that source code, which works really well for a parser. Unexpected end to bracketed expression. Expected that. And now we don't need the assert anymore. Pattern does not mention field offset. That's fine. I don't need the offset here. Same thing here. Don't need the offset. So we have atoms, we have groups, we have prefix expressions. So now we've read the left-hand side. Next, we need to read whatever the operator is. And what we're going to do is we're going to peek at what token would come next. Like if we read from the parser, if we read from the lexer, the next token, what is that? Because we don't know whether we want to consume it yet. It could be, for example, that this is a just return the left-hand side. We should not be giving this thing up because there is no operator that comes next. Like for example, if the next thing that comes is let's see if I can dig up the original code here. If the thing that comes next is an end of file, then we're done. We should just return. And we should only continue if the thing we find next is an operator, because that's always what should follow a left-hand side. Although... what about the case where there is no operator? Like, what if the program literally is just a literal? How does this work? Oh, then your peak would return nothing. Right, and if the program has anything after a literal, then the next thing must be an operator, because you didn't have a left-hand side operator. Okay, great. So what we want to read out here is we want to look at what the next thing is. Now, this is going to be a little awkward because we're using Peekable, which is an iterator wrapper in Rust. And the Peekable thing, pretty naturally, is it calls next for you, and then it sort of saves what that thing is in a temporary storage location. And then when you call peek, it gives you a reference to the next item. And that means that it's a little awkward to hoist the result out of there. I wonder if is there a peek mute? Yeah. So I think actually what I want to do here is if op.mapOr false, op.isError, then self.lexer.next.expect. Checksum above dot unwrap error. Checked error above. Turn error of that. Wrap error with looking for message. And I suppose up here too, we could do, it's not actually shorter, but it feels more right. Expect error. And so now, if we get here, then I think we can dot expect handled error above. Oh, there's no transpose. That's fine. We can map it instead. We can map here the res and say res dot expect. So if the thing is a none, then great. Otherwise, now we need to look for anything that is an operator. So what are the operators that we want to handle here? Because if you look at the original, it has the lexer already sort of categorizes things into atoms versus operator. So you see here the tokens we get out of the lexer are atom or op. And so down here, when they peek at the lexer, they look for op, and anything that's not op or end of file panics. Which is not a thing that we've done. Like, we just have a flat sequence of tokens. We could actually improve this, right? So we could, in our lexer, and maybe this is a good restructuring to do, we could actually have an op token and a atom token. Right, and say that some of these go in one and some of them go in the other. And so every token kind is either an op token or an atom token. And now braces are ops. And like comma is ops, but this is weird to me because these are ops at a very different level than the parser thinks of ops. So I'd rather not overload the nomenclature. So I think we're going to stick with just having one token kind. But that does mean that here we actually need to look for specifically all of the things that are either infix or postfix operators. And we need to look for them explicitly. So what are, if we go back to our lexer here, what are the things that are postfix operators? Well, we know that left brace is now, right? Like, that's one thing we discovered, because left brace, if you have the left brace as a postfix expression, then it is a function call. So left brace, definitely, which sounds weird, but is. A comma is not. A dot is, because a dot is field access. So token kind dot. A minus can be. Oops. What else do we have? Oh, sorry, left paren. You're totally right. Paren. Token kind plus, yes. A token kind. This is where it gets interesting. So a semicolon arguably is, because it is how you separate the statements of a program. So it is arguably an infix operator, just like comma is in a list. So there is an argument here for program being a token kind or being an op. And it is a semicolon separated list of arguments where the semicolons are where the semicolons are infix operators in between. But that feels weird. Let's get back to semicolon later. But plus is, star is, and all of these are. What? Oh. What else we have? We have equal is equal one? It's an interesting question because like in a way, equal is just noise. You could just as well write var a and a value. And I think the equal is only there really as a kind of grouping operator for to help determine the precedence. But okay, and is one. I think equal might not be. For is one. Although for is a, now that I think about it, isn't for a prefix operator? For is another one that's weird because it comes before its two operands. Right? It's for condition block as opposed to condition for block. Which I suppose it means that it is a... it means that parentheses are both an infix and a postfix. Right? It's an infix if the first operand is literally the name for. Interesting. And same with variable assignment, right? Variable assignment is weird because it is 4 token trees for one op. A statement is anything separated by a semicolon in this language. So like variable assignment, for example, is var followed by ident followed by equal followed by expression. And that whole thing is a statement. So maybe then actually... I suppose then the other way to structure this is that semicolon is an infix operator that separates statements. Or in fact, a postfix operator that separates statements. I think maybe I'm getting ahead of myself here. I think it would be... For is a prefix. But I guess what's weird to me is a prefix expression feels like it ends up just taking one operand. But I guess for's operand it's almost like for is a prefix operator whose operand is curly brackets as a postfix operator to a bracketed expression. Which just feels wrong. Yeah, it feels like it just needs special handling here. I think that's probably what we need to do, is that we need to handle it as a special kind of group. Because it's not a left-hand side, right-hand side kind of operator. I think that's what we're going to have to do. So in that case, what I'm going to do is here, I'm only going to handle infix operators. So if we go back here, infix and postfix operators. So that means and, if is going to be special, class is special, for is special, fun is special, if is special, nil is an atom. Oh, nil we don't handle up here, right? I think we forgot nil. Or is not special. Return is a prefix expression. Right? Prefix. What else do we have that is an infix operator or a postfix? Super is not, this is not, true is not, var is not, and while is not. Because I think these are our infix and postfix operators. And I think this language probably doesn't even have a postfix operator, unless it supports like factorials, which, I mean, maybe it does, but so then maybe let's handle these as groups. So 51, no. So if what we find is a so these are ternaries, and I think actually there was a mention of this in the article. So if you look at yeah, here, like the ternary operator is a 3-argument thing. And so I'm curious actually how that's parsed here. Oh, it's parsed as, I guess it is infix actually in that case. So we're going to handle it specially as a, so they're not really ternaries, but this is prefix 2 arguments, which is going to be for and while and not functions, because those are 3 arguments, right? Function declarations, I mean, because they take name, parameter list, and block. So those takes 3. Class just takes name and block. So as weird as it sounds, class is 1. And I think those are all. If without an else. If without an else is an interesting one, because I think that has to be handled under the if with an else, and then you just break early from it. So let's see how we would handle this. So we don't need to look for a terminator here. Instead, we look for the first and now we don't need to ask the lexer for a thing after either. That's not relevant to us. So we do first and second, and then we match on the kind for what we produce. And then we're going to produce a, what's the expression here? It's a token tree cons. So cons here just means some operator with a vector of arguments, where that is op and a vector of first and second. And the kind that we care about here is if it is a token kind 4, then it is an op 4. If it is a while, it is a while. And if it is a class, it is a class. And anything else is unreachable. And so this is now up here. This is the operator we're looking for. Op, and this is the 0th argument. And op, first argument. And then here we're actually going to do this in op expression. Like so. For loops. Yeah, for loops take 4 arguments. That's why they're called for loops. That's funny. Yeah, so I mean, that one's pretty straightforward, right? It just means that you need to parse out multiple arguments. And then the triple case is really just var and... So if is condition block yes, it's condition block else block. So that's 4. So function definition then is, I think, the only other one. And so here a var and a fun, first, second, and third. And I guess actually we should really do these in order, right? So it's unary prefix expressions. Prefix are, and instead of saying doery, prefix 2 arguments and three arguments. And then this is going to be 4 arguments, which is going to be for and if. Now, these are going to be a little bit interesting because for functions, it's pretty easy. For functions, we don't need to check any of the tokens. However, for variables, for variables, the first should definitely be an identifier, and the second should definitely be just an equal sign. Which actually means that we could here say expected identifier. So if LHS.kind is equal to token kind var, and first, and not matches first. So that's supposed to be token tree atom atom ident. Right? Then here we can actually return a sort of I'm just gonna to do this one for now, just because I want to structure this a little bit more. Why is this sad? Yeah, so we need to do a bunch of parameter checking here. So for var, we have to check that the first thing is a variable. And then we also need to, so we can keep this one here. If this, then sadness. But also, we don't actually want to parse the second argument. We know it should just be a single token, which is an equal sign. So arguably, it doesn't really belong in this 3 argument category because it should just be a 2 argument category with a special case here. So see, so it should actually just be up here where after parsing the first, it must be an atom, but also we're going to self.lexer.next. So we're going to walk the lexer 1 token and say it must be an equal sign because this is a variable assignment. And then we parse the second argument because there is no, like, equal sign is not an argument here. It's just a thing we require in the parsing. And so it's going to be one of these, which is not super nice. I wonder if there's a nicer way for us to do that. So if the token.kind is a token kind equal, then we're good. Otherwise, we can say expected equal. Yeah, we're checking here whether it's an equal sign, right? We're not just skipping it. But we do also need to skip it, but we need to check that it's an equal sign. So if it is not an equal sign, expected equal, and then we say malformed variable assignment. And then this, I think I like better than what we had up here. Okay, so we give a nice error there. And the looking for here is a little bit weird because it's not really... Yeah, it would be nice here if the Lexer, and in fact, the Lexer can have this, right? So we could say, it's a good suggestion that in our Lexer, we could do, in fact, that's going to be way nicer. I like that idea. We can take this whole pattern right here and we can have a expect, which is a mutable reference to self, and it returns a result of nothing and a Miette error. And it is going to do self.next. Next, which should be a token kind. In fact, it could be a function, but let's say token kind for now. Then okay. So if we hit a token that's not the one we expected, then we say expected next, unexpected. And we could actually be a little nicer here, right? We could make this a macro actually, because we do want this to be a literal. But absent that, we can just do this, I think, and then say error. So expected can be a stir here. Expected. Or I guess unexpected. So that's going to return this. And we do have to bring in that. So now we have an expect function that we can use, and it doesn't... we don't have an end of file here, an end of file error here. So I think we're going to have to lift that from out of here, which kind of makes sense anyway, I suppose. Where's our end of file error so I can import it? Might not even need to import it. So expect here. Into. Oops. Into. Could also move expect to parser. I could, but it feels right for it to be on the Lexer actually. And so then we can do self.lexer. Is there an inner on Peekable? Oh, that might be our... I thought Peekable had a way to get at the inner thing. Oh man, it doesn't? That's really unfortunate. That means we can't really use it is the problem. It means we actually need to... it means we actually need to have Peekable be a first-class property of our Lexer, which is fine. It's just a little annoying. So we can do peaked, which is going to be an option of an option of a result of a token of DE and a MET error. So peaked is none. And then we're going to add a pub fn peak, which returns a option result token DE MET error. And that is going to be if let sum peak is self.peak, then return self.peak .asref. Otherwise, we're going to hit a borrow checker here. I'm fairly sure we're going to hit a borrow checker here. Self.peak is equal to self.next, and then return self.peak. What? Oh, actually, maybe I can get around it. If self.peak.is sum. Wait. Oh, peaked. I think I called it. Self.peaked.asref. Like so. So now we have a peak. And so now we can go back up to our parser, and we no longer need the peakable because our Lexer is directly peakable. Like so. And so now down in here, we can do expect terminator. And then we can even give this as sort of a better explanation of what's going on. And we can do that. And we can question mark. And we could wrap error looking for message. Lexer peak is peak one token, not peak one character. So now that we have expect, now we can do the same thing here, which is we're going to do token kind equal. Like so. Beautiful. And I suppose actually it feels kind of weird to pass in this because here we already know what we're looking for. So I think this looking for is just wrong. I think this should be the caller's responsibility. So here we're just going to say parsing left-hand side. And then this doesn't need to pass anything down. And then the wrap error here is in bracketed expression. And then this is actually just going to say on left-hand side. And this is going to say after bracketed expression. Yeah, this feels much nicer. So the wrap area here is in right hand side. This goes away, and this is now in first argument of this, right? And then this will be here in second argument of this. And then this can now say in variable assignment. Why is it necessary to implement peek instead of using peekable? Because peekable doesn't give us access to the underlying the thing in the Lexer, the thing inside the peekable. You can't like dereference the peekable to get the inner thing, which we need in order to be able to call something like expect on it. Okay, this now looks a lot nicer. And then this is, and I suppose we can just grab it from up here now. So this is here, and here, and here, and this is now second and third. And then this argument goes away, and this argument goes away. Okay, so var is an example of something that only really takes two arguments, and one of them is just kind of a fake argument. The other things we need to check here is we need to check that for for and while loops, we have to check that the condition is surrounded by a parenthesis. So if LHS dot, I guess we can do matches. LHS.kind is token kind for or token kind while. Then self dot. This is like an assert peek. For loops in this language are here. I'll show you. Oh boy. Here maybe. Like this. So we want to, this becomes sort of like an assert peek, right? So I think actually it's a good question whether we want an assert peek or whether we just want to inline the parsing. One of the challenges we have, right, is that, and maybe the way to do this is to, like currently for groups, we just output the left-hand side as a, we handle parentheses as just a, it just gets replaced by whatever the inner expression evaluates to. But you can imagine that we preserve the group. But that feels awkward because like it would allow us to do like the for condition checking later, for example, but it feels like it should really happen here. We could special handle the entire for loop construct. I suppose that's the other way to do it. And in fact, maybe that is the way to do it. maybe we don't treat it as a construct the same as the other. Yeah. Just kind of sad is all. Right? To like have to special case all of these. But I suppose it's not that bad. Right? But it just makes me sad to do this. Right? 4 is now its own special one. It takes a... It does a... I guess it's a... Oh, maybe it's not that bad because it's this. So we expect a left paren in for loop condition. So we expect that. Then we have the condition. And actually, that's not quite right either. Because it's not the condition. It is we expect first the... Yeah, I think the question, right, is whether we want the A's, and someone pointed this out in chat, whether we want the A semicolon B semicolon C inside of for loops to be a specific construct that we've set up for loops, or whether we want it to be just a block that gets executed as a condition. And I think these are actually treated as like 3 separate things that are special in here. So in that case, it is like the initialization, the condition, and the incrementer. And in between each of them, we expect there to be a semicolon. In init condition of for loop, in loop condition of for loop, and in incremental in the incremental condition of for loop. And then we expect a right paren. And then we don't need any of these. And then we expect a right paren, and then we expect a left brace. Yeah, maybe it's finisher. We'll leave it like this for now. In for loop, so we expect the left brace, and then this is the block in block of for loop, and then we expect a right brace. And now this is a token tree. Nope, it is an op for loop, which has init cond inc block. So it's not super pretty, but it's not the worst either. I suppose we can just do, and then we do the same thing for while, except while is a decent amount easier, which is this. So a while is, we expect a left paren in while loop condition, in condition of and I suppose many of these now don't have anything to print in there anymore, so they're actually a lot nicer. In loop condition of for loop. the language here feels artificial. Like so. So that's the for loop. And then for the while loop, it's in while loop condition. In while loop condition. Then there are no more things there. So it's a right paren. And then it is a left brace. And then it is a block in while loop. And this should say this. And same thing here. And now this is a while with just condition and block. Okay. Class is actually not special at all. I suppose actually we should check that it, just like for var actually, they both require that the first thing is an ident. And so the way to do that is probably this in first. Yeah. This is actually going to be quite nice, I think. And then it'll be token. And so we just modify expect here to return, instead of a result, it's going to return the token. Because why not? Right? And now we get the token back from this. And this really we know is an ident. So we can just say that this is... that ident is atom ident token. I guess here, right, we can even do let token kind ident. We don't even need to. We can even assert equal here. Token.kind. Token kind ident, right? And then we can here just do origin is that. And so now this is the ident. And that's the case for both class and var. And it also has to be a token tree atom. Okay. So we have, and then we have var. Wait. I thought we already dealt with var. We already dealt with var. So we have function definitions. And function definitions are a little bit special here in that, or they're a little bit similar here in that they first take an ident. And we can actually change this up here too. In name of that, in name of function, and then it's supposed to be the parameter list, which it's an interesting question whether the parameter list we should just let it be treated as a, no, we gotta parse it. I think we gotta parse it. Because it's a comma separated list and we don't have a notion of lists here. Expect is moving the cursor. Yeah, that's the idea here. I think we do need to parse it because the comma separated list is not a structure we have anywhere else. And so what that means is, let mute parameters is a vec. And then we're going to do this. So we're going to expect a left paren in function parameter list. That means we don't need the width, right? And in fact, it's the same thing here. Don't need the width. Whoops. What did I do? This. So we're going to do left paren, and then I suppose what we have to do is do a loop here where we are going to call we're going to peek. So while self.lexer.peek.map or false. Next. So next here is an error. So map or false. Next. So this is like the outer thing that we get from peek is an option. If the option is none, that means we're at the end of the parameter list and we might as well stop the loop. Otherwise, we do have a next token. If that next thing, that might be an error, in which case we map to false because we know we should enter the while loop. Otherwise, this is an okay, so this is the actual token. Then if the next.kind is equal to token kind right paren. So while it is not equal to right paren, then we keep parsing it as a parameter list. So then we parse a parameter. And I guess we could do here, we can actually pretty nicely say in parameter of function, we can even print the name, right? Like we can even here say of function name in parameter number, that's going to be parameters.len plus 1, because zero indexing on parameter list is weird. So in parameter number 1 of function by that name, and this is where it gets a little bit weird. Because we're not actually expecting a comma, we're expecting a comma or a end paren. So I think expect actually needs to be an expect if. So we could do expect where this just calls self.expect where unexpected. So that's going to be, so this is expected. And so next dot kind is equal to expected. And then next here is an impl fn mute of a token de to a bool, and check. Right? So now we have an expect where, and we could do expect where token dot kind. We could do a matches here. Matches token dot kind is either left right paren or comma. End of argument lists. Or I guess this is parameter list. Continuing parameter list. In function parameter list of. Here too we can be helpful. So we choose to be. In parameter list of function that. So this actually gets a little bit weird. Wait, did I do something wrong up here? Oh yeah, you're right. This should be ident. That means this should be ident. No. That means... Yeah, this should be ident too. Missing... Oh, so this should actually be identifier. This should be expected identifier. Same thing here. Good call. In function name declaration. In parameter list of function name. We're going to have real good errors in this random parser we wrote for a language we're never going to use. But hey, and this actually, we want to look at the token. And if the token dot kind is equal to token kind right paren, then we break. We need the break in addition to the while loop because the while loop is whether we should even enter the loop. So I suppose we could do like an if there. But I think because you could have this be the parameter list, in which case you don't want to parse the first parameter. Check for immediate parameter list end. I suppose we could peek actually. We could just say if this is immediate parameter list end, else, and then we just do a loop. That looks a little nicer, I think. What did I do wrong now? Here. And I suppose I might be able to just do a if this matches some okay token kind this. And that's a lot nicer. Yeah, that is a lot nicer. Okay, so if the if we peek and we immediately find a right paren, then we end the parameter list. Otherwise, we loop trying to read parameters and the separator until we hit a right paren, at which point we break. But of course, this parameter needs to be parameters.push parameter. Is sort of the whole point of them. And then now, after we've done that, the next thing that we expect is we want to pull out the block here, which is one of these. So we expect a left brace for function for body of function name. And this is in the body of function name. And now finally down here, we can say that this is a function definition with parameters and body. And parameters is going to be wrong because this needs to be a token tree cons. Although that's a little weird too. We don't really have a... I think function definitions maybe can't be a cons unless we have a notion of a list. Yeah, it's not a bad idea to make a function for parsing a block, given we use it a couple of times. But it's only really 2, I guess 4 loops as well. But I like the fact that we can easily give them nice looking error conditions too. The question here is what type to return here. It might be that we actually need a separate token tree type for fun. I think we might. And at that point, it really is this. Although I'd like to keep the span, which I think means this needs to be a token DE maybe, that we just have already checked is an ident. So this is then this, right? But I suppose it can be an atom. I think that's fine. So it's now a this, and a this. And in fact, the body is not a vec. Oh, I guess the block is the body, but that's fine. And it's unhappy about this because it found token tree, but I think this one we can just not make it token tree once we sort of specialize it like this. Okay. And now I think 4 is no longer here because we're special casing it. So it's only really if left. And if we can handle, if is really just a less fancy 4. Oh no, but it has else. Okay, great. Fantastic stuff. So what we're going to do is we're going to take a while. And we're going to say down here. So this is not really 4 arguments anymore. This is just, at this point, it's just custom operators. So, in if condition, and the condition is, we need to have the if, we need to have the end of that, we need to have a block, and I agree at this point we really should just have a, helper for blocks. All right. Fine. Pub fn parse block. You are not wrong. So down here, parse block. And then I guess context is a stir here. Right, this, okay, of block. And then let block can now just be self dot parse block. At which point it doesn't need to wrap error anymore, because that can happen at the caller instead. And the error will already sort of indicate that the problem is a missing this or missing that. So now we can just here say parse block with wrap error in for loop. And this is now in while loop. And this is now with I know that was an if, but I want in here, I want this as a body of for loop, and this is now in body of if. Okay. So this whole like 3 arguments, 4 arguments is all just a straight up lie at this point. So we're just going to get rid of it. These are more like special cases. Special expressions, if you will. Okay, if. So in the if case, we now need to see, where's our little peeker? Right here. If peak is an else, else is, otherwise is none. And then if we do have an else, then we do this. Well, we can really do lexer.next because we know that we've peaked here and saw some okay. So there's no need to check the return value in body of else. So we just grab the else here and we can then say otherwise is some of that. And then I think if maybe also needs to be special because we need to handle this sort of optional case. Right, so fun, and then we have if, which is a token tree and an option token tree. And a token tree for the condition. So if is cond, and then block, and then otherwise. Whew. Okay. I think now maybe we have all of them. There is an interesting question of whether, for example, we should have special ones for things like classes, right? Because we know that the first thing is an ident, and so it's kind of weird to put it as a like just any operator where it just so happens that we know that if the operator's class, then the first argument is then the first argument is an ident. So we got to think here about whether we want stronger typing there. I'm going to not add it for now. Oh boy, it has a question mark colon as well. That's fine. Control flow. Can it have arbitrary else ifs? I don't think it can. And if statements execute one of two statements based on some condition. So it only has if and else. But I'm going to not strongly type things like for loops or classes and stuff for now. And then we can think about doing that later. Oh, it's getting late. Okay, let's see if we can get somewhere useful though. Okay. So we've read the left-hand side, and it's interesting what we want to happen next, because if you think about it, it doesn't really make sense to, like, it doesn't make sense to allow like a class to be used as an expression or a var to be used as an expression. These are really statements. So I think we're actually in a slightly weird case here where parse within really parses an expression. And I think we need a separate parser one level up that is a statement, and that the statement parser, or an item parser maybe, that will not look for another operator. It knows that it should only get individual statements, where we can think of class as an example of a statement. So that makes me wonder. Yeah, I think parse within currently is an expression parser. And that's what makes this kind of awkward, which is, or it makes it kind of weird, because we now have a, like, these aren't special expressions. They're just straight up statements. So I think we maybe want a, I think we may actually want a whole, stay with me here. I'm going to copy this entire thing and say this is now parse statement within, right? And then this is parse expression within. And when you parse an expression, you can have left and right braces, but you cannot, and you can have prefix expressions. You cannot have return, and you cannot have print. Right? And for does not live in the expression parser. Oops. While does not live in the expression parser. Class and var do not live in the expression parser. Fun does not live in the expression parser. If does not. So now we're back to this, which is much smaller. And then up here, so in the parse statement within, This, I think, should never encounter an atom or a group. It can encounter print and return. And the various other things that we've talked about here. But the right-hand side is a parse expression within. Init is parse expression within. Condition is parse expression within. I think now we're onto something. Increment is parse expression within. And parse block, I don't know yet. I think parse block is parse statement within. And maybe parse statement within should actually be parse statements, and it will look for the next semicolon delimited thing. So this is parse expression, and block is parse block. Should we have a special loop block case or not? I don't think so, because I don't think locks has those kinds of things. So class and var have a name and a block. So this is not second. Oh, var, damn it, var, they actually do vary because they're not the same. A class takes a block, whereas a var takes an expression. So this is parse expression within. So this can now also say, which is quite nice, in variable assignment expression. And so this is now op var. And this is now in variable assignment. But for class, this is parse block. And so this is in class definition body, class name, in class definition. And then this is block, and this is op class. So we could definitely do like stronger typing here for a lot of these, especially at the statement level, because like for a while we know exactly what constructs these should have. But while class, var, fun, the parameters here are expressions actually, even though they're really not, they're type lists. In fact, they are lists of identifiers. They're not even expressions. So arguably this should like be a parse ident. In fact, we can make it be that because we can just say, we can just call the lexer directly. We can just match on self.lexer.next. Right? And if that is none, this is sort of a special case of this. If it is none, then we return EOF dot into let parameter is this. So if we get a sum of error, then we do that. That's fine. And I think what we actually do, and this is going to help us a little bit, I think, is if we get a kind that is token kind ident origin, then we're happy. If we get any other kind of token, then we expected identifier. And I think this maybe just goes there and there and here. Right, so the idea here being that we sort of construct a, oh, where did this go? Why is this so long? 2. We just directly look for an ident in what comes next from the lexer. And actually, what am I even doing? If we know that it's that, we can just use the lexer expect. That's what this was for. Clearly I am now actually getting tired. Token kind ident, otherwise expected. What is it even supposed to say here? Unexpected parameter listing. Unexpected parameter. It's an unexpected token, really. Unexpected, whatever. Token for now is fine. And then all of this can go away in exchange for this. To this. And there. Oh, okay. And so now we know that the fun that we get back here, this can actually be, what do we give it back? A token of D. Because that's what we actually get out of here. Because the parameter list is not a list of expression, it is literally just a list of idents. Like the names of the parameters. If this is parse expression within, that's parse block. And then when we parse statements, there is no loop afterwards to check for the right-hand side. Right? At least I think that is true. So I think we actually just match on the left-hand side. And it's not even a left-hand side, it's like it's a first. Although, is this going to get really weird with function calls? Because function calls can be part of expressions, but can also be a statement on their own. So I think actually we do have to say that all other cases are going to fall back to calling the expression parser. Right? Did you make next and Lexer update the peak value? I don't think I did. It's a good call. Ugh, no. 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 Peaked. Yeah. I think maybe we need to allow, in the statement case, we don't want to allow arbitrary expressions, I don't think. I think we just very specifically want to allow we want to very specifically allow idents and that might be it. No, and parentheses. Because I think we want you to be able to write, a whatever. We want you to be able to write a dot foo, and we want you to be able to write a dot foo or even a, right? So I think it is specifically a left paren, I think we want to allow, and a what's the other thing? Okay, now we're getting to the tired phase. A left paren and a ident. We both want to allow. And an ident is trivial because it is just, and this is sort of gets at what we do in parse expression within. Parse expression within, right? If we find an ident, then what we produce is just a token tree ident. So that's easy. And a left paren, I think we just do the same thing as we would do down here. But I think we only allow left parens here and not braces. It's a little unclear, right? Whether should you be allowed to write a dot foo or a. I don't think so. It's interesting how like the decisions we're making at a source code level here translate into implications for the language. So higher order functions are possible. So this is fine, but that still ends up being this case, right? Where you have an ident first that sort of starts the chain. So yeah, I think that's still fine. So origin. So here, why not just allow arbitrary expressions for functions? Also check the correctness during evaluation. We are going to have to check a bunch of things later on as well, but sort of at the parsing stage, we still want to eliminate some sort of obvious cases that we want to disallow. Arbitrary expressions for functions. I don't think LOX is an expression language. So I don't think you can have at least I haven't seen anything that suggests that you're allowed to do, for example, var x equal if true, the same way that you can in Rust. Else, whatever. I don't think that's a thing you can do in LOX. In other words, like, statements are not expressions. And similarly, I would not expect you to be able to do, for example, if true, else, and call because each branch returns a closure. So I think if the thing we see first is an ident, we need to handle it because that's a statement is allowed to start with an ident, and similarly, I think a statement is allowed to start with a left paren. And then this is inside of there, though. There has to be an expression. And this. Okay. And I guess, sure, this can stay LHS. But then I think in the, so in these cases, we have to fall through. In this case, though, I don't think we have to fall true. But that's an interesting question. Because if you write like, I'm basically trying to figure out whether we can early return here. Which feels like we should. Yeah. Okay, and same thing with a 4. I think we return okay. Right, for these we don't, because we have to handle the function call case. For this we do, for this we do, for while we do, for class we do, for var we do. I think it's actually for like all of them except for the, yeah, it's everything except something that could be an expression. And the only expression we allow here is those to start with ident or paren. And then this, let's be a little bit better and say here that we return error. Miet. And then I think here, what we actually want to do is, where's our expect again? Here. So here we can say expected start of or I guess really it's unexpected token, expected start of expression. Now, I think I've messed up in that this actually needs to be this. Because I don't think that one is automatically interpolated. Yeah, this should be a token. Great. So that way we give a nice error if we expected a statement, did not get that. You are totally right yet again that my next is now wrong, which is if let sum next is self.peaked.take, then return sum next. Totally right. Okay, so this is now the postfix case for statements. And so here we look up whether we have, if the next thing is an error, then we return it. And I suppose we can do something nice here, like in operator, in what do we even say here when following, when after, in place of expected operator. So weird looking error, but we'll take that. So then we look at what comes next. What is the operator? And I think in this case, in the statement context, the only things we allow for what comes next are parens, dots. I don't think we allow minus or plus or star or bang equal or equal or less equal or less or greater or slash or and or. Or no, we don't allow the super or this here either, but we do allow those up here. Oh boy, as idents. So here. And those I think I missed from our parse expression. Yep. And that also means that down here, no. So we allow the paren because it's supposed to be a postfix, and we allow the dot because it's supposed to be a dot. Although this gets weird if you have nested parentheses, right? No, because those are already handled further up. This is the thing that comes after the end paren. Okay, so we're good. Bad token we do better than later. Postfix binding power. That should indeed take an op. And the only postfix operator we have I think the only one we have is This shouldn't even... Oh, I guess actually there is a fun which is... There is an op which is call. And that's what... That's what this turns into. So a left paren here turns into op call, and a dot here turns into op field. Yeah. So I would love to show you how they're parsed on the command line, but we don't have a thing that compiles yet. And so once I have a thing that compiles, I'm happy to show you. So call is a postfix and is the only postfix that we have. Infix is op Yeah, I need to think about these, but this is op field. You can do the ones that are immediately translate at least. Star op slash op plus op minus. Yeah, this is for ternary. Should probably just have implemented expressions first. You're not wrong. I shouldn't have done statements at the same time. But hey, it's the same thing we did for the tokenizer, right? We decided to tokenize everything. This file's getting long too. Parse. So this is actually going to call parse statement in a loop. But for now, we're just going to have it parse a single statement, I think. So this is like to do in a loop. And this is to do in a loop with semicolons. Depends on class versus body. I think it does. Like I think the parse block for a class is different than the parse block for a for or while loop body or a function body, but we can deal with that later. Okay. So self.lexer.next. So this is if we discovered that this is a postfix operator, then... Oh, this is for array access. We don't have arrays. So that's easy enough. We do, however, have, and this is where it's a little awkward, when you have a function call, I guess we have op call. Then we need to parse the argument list. And so this is sort of similar to... this stuff that we wrote for parsing the parameter list, except that we're going to parse expressions instead of idents for 40. Yeah. So down here, arguments, we're going to grab a thing out of the lexer, which is a left paren. Argument list. In argument list of function call. So at this point we know it's a function call. Argument list length. Let argument. And now this is no longer quite that. This is now what we used to have, which is let parameter is self.parse expression within with a 0. And then this. Right, so we parse one expression, which is the next parameter. an argument. They're arguments when you're calling. I know. Okay, and so now argument, nope, argument. So we parse out an argument, and then we expect to get either a right paren or a comma. And then this is now an argument list of function call. So now we have that. We've eaten the right paren as well. And so down here, we now have the function call. And so this now can go away. And this now is a op call with a... And I think what's nice here is this can actually just be arguments. No, it cannot, because it needs... This actually does need to be different, because this has both the left-hand side, which is the function to call, and arguments, which is the... this is the function to call, and this is the arguments to call that function with. So call has a token tree and a vec of token tree. Oh, left-hand side is just a token here. That doesn't sound right. Why is left-hand side just a token here? Oh, because this needs to be left-hand side is equal to that. Okay. Oh boy. This enumerator takes 0 arguments. That means I messed something up. I messed that up. Okay. And then we look for... so this is for just unary postfixes, which we don't have any of, so that's fine, but we'll leave it in. Infix. Do we have any infixes for statements? I don't... Oh, we do. We have field access. And ternaries we don't, because that's only an expression context. So it is only for field access, which means we can get rid of the ternary code here and just say that this is... Why is there a continue in here? This is parse expression within because we're parsing the right-hand side of a field access. Actually, that's not even an expression. I think it has to be an ident, right? If you're doing field access, I guess we might as well leave it an expression. We can do that later. You also need the function. Oh, that's from earlier because of the break. Where's the... Oh, right. It's so that means this needs to be a mute LHS because we're going to keep looping. That's right. And then here, this is going to be wrap error. And I think we're nearly there now. This is the... this is in the right hand side, right? Because I think for the left hand side, we actually say, oh, on the left hand side. We can do on the right hand side, I suppose, to make it. And then something's complaining about something up here. Cannot move out of rest because it's behind a shared reference. Oh, that's fine. That's just a asref. Missing. Why is a function call parses a statement? Isn't it an expression? It's both is the problem. So currently, so right here, we're parsing the statement version. And then we're in the expression parser, we're also going to have to parse it to be used as an expression. But you can use a function call as a statement as well. And so that's why it needs to be handled in both. So now we're in our expression parser. And so now we're basically just going to have to fill this in the same way. So for the expression parser, it's actually interesting because I don't even know if in expressions you want to allow curly braces. I think actually you don't. I think you only want to allow parentheses. I think the braces are just for blocks for us. So this is sort of a leftover from earlier, or from Matclad's version. Okay, bang and minus we do want to support, and those are parse expressions within. And those are the only unit prefix expressions. Then we have here, so this is going to be just like in our other one, like this. And in expression context, we're going to allow left paren for function calls. Dot is fine for field access. Minus, plus, star. These are all fine in expression context. But we need to map them to their corresponding operators. Unless we say that we're just going to use the token kind, but I don't love that. So I think actually here we do need to map each one. So like this, for example, is a call, and so on. Oof. It's going to look nicer after formatting it, I think. Oh, I could have made this way better for myself by having it actually use the expression from earlier. That was annoying. Okay. Right. So here, QA. There we go. And then it doesn't like something. Where did I mess up? Here I messed up. That doesn't look super pretty. This might be a good place for a macro. Okay. Do we have anything? Right, so here we actually do need to have the same logic as we do for statement within, which is pretty awkward actually, because that logic is now decently long. So this feels like we probably want a function call parser here. So let's go ahead and add that. So this is going to be parse fun call. So we're going to go down and grab. Where's my function call parser? Where is my function call parser? Fn parse statement within. Oh, this file is getting real long. So this needs to be self.parse fun call. Boom. Excellent. Actually, I suppose that just returns the arguments. So this should be a vec of parse fun call arguments. Fun call. So this actually is going to be this and parse fun call arguments. In function call argument list. Yeah, and now that actually looks pretty nice. And then parse expression within now can just do the same thing where this sort of becomes a else if, so we can really just match on op here instead. And we don't have, this is like to do ternary. But we do have op call, which we want to do this to. And then we have everything else, which we want to do this to. And this is parse expression within. And so here we have parse statement on the right-hand side. Like so. And this just is self.lexer.next. Postfix. Oh, did I mix up my... I did mix this up. Parsed. I mixed something up. Yeah, that should be in postfix, not infix. That should be up here. Where LHS, oops. Here. And there's no ternary in there. And then this infix is where we want the ternary. We don't have a ternary at the moment, so that's just going to be on the right hand side. And this is a postfix, so there's nothing to parse. Okay, great. I think we now have that. This is asref. There are a bunch of things we could probably share between these, but I think for now it's okay. What happens if I just run this now? Parse cycle. Cycle at 651. Right. Infinite recursion. Yeah, I'll make sure to push this code somewhere as well afterwards. And here, really, I can use fields here, right? Like this is condition, yes and no, instead of true and false or else, because that wouldn't work. Option box, and here too we could do name, parameters, and body. Call, callee, and arguments. Name, parameters, and body. If is now condition, yes, and no. And this is, I guess we'll map that to a box new as well. This is a box new, this is a box new, so that it's sized. Oh, I think we're getting pretty close here, because looks like I'm running out of compiler errors. A function call is a function definition, I suppose, is, how do I even want to print that? Def name, and I guess this, right? And then parameters. Oh, maybe it is just this. And then parameters, print, and then the body goes at the end. Isn't it fun that you can print everything as you can print everything as expressions? Impl display for atom. Match self. And I guess when displaying these atoms, we can just do, right, S. Right, F. F nil. Right, F. Do Booleans implement display or just debug? It's an interesting question, I think. Okay. Oh, I have to do the same thing for operators? Oh, I guess so. That makes me sad too. The strings can't contain special characters because this is locks. As we discovered, oops, no, that should be up. As we discovered, locks strings are actually very simple. Okay, this feels like a job for this. And so now this can be... Oh, okay. Oops. Oh man, I'm losing the... I'm losing the steam here. I can feel it. Less, greater, slash, bang, equal. Wait, equal isn't even an op. Equal is not an op. If is not an op. For is not an op. Right? Because, or did we end up making for special? No, for is an op. Class is an op. Fun is not an op. Print is an op. Return is an op. Field is an op. Call is not an op. So let's not be lying. Var? Var is an op. Okay. Function definition is that how do we want to print a function call? A function call is just just a callee followed by the arguments printed individually, followed by this. And an if is a little bit weird to make it a an S expression, arguably, but so we want I guess there's no real reason for it to wrap these because I think you get the wrapping when you call it nestedly, so that's fine. Yes, and then if let sum no is no, then no. Also, why is this not using nice syntax? Also, why isn't this called A? I just want to get to the point where I can run this on a program and get something out. Okay, so postfix is call, I suppose. I guess we did add a call in there. But call doesn't really have an op, right? Like we have it there, but we never actually print it, I don't think. Because it ends up turning into its own thing. We just need it in order to represent it for the postfix call. But that's fine. Oh. Call is never constructed. That doesn't sound right. Do we truly never produce that? I suppose we don't. Wait, so then why did I even add parse fun call arguments. Well, first of all, this is wrong because it doesn't include the left-hand side, which it needs to. So this needs either we need to extend the same vector, or this needs to be call and it needs to be special. And I think I want it to be special. Arguments. And that also means that the other place where we call this is similarly broken. Wait, I did something wrong. Match op. Let's make these actually be the same. That's this. And anything else is this. There we go. All right, delimiter is never used. Great, that can go away. Token tree should be pub. I agree with that. Origin is not used. Origin is not used. What else you got for me? No other diagnostics except in Lex line 1. Okay, that can go away. Unterminated string. Okay, let's see now. Let's write a little locks program. A.locks. And it is just going to do hello world. Because we can only parse a single thing anyway. And we're going to parse A.locks. That's true. Tokenize and parse. So what is parse going to look like? Parse is going to look like this. It's also interesting because I think what we're going to need to do is print this tree according to how the sort of book says that you should print the AST, which is fine. We can do that. It's just, we're just going to have to actually do it. Okay, we're going to read out the file, and then we are going to do let parser is parser. That's not the place I wanted the parser from. I want my own parser. I want parser as underscore and subcommand as underscore so that I get my own parser. Oh, really? Okay. Fine. We'll do that. And then this will be Lex. Actually, no. We will do this as impl or imp. And then we're going to do here imp lexer. Imp lex, and imp parser new of file contents. And then parser.parse. And we're going to want to match on this or something. But I think right now I'm just going to unwrap and then ePrintline what the token tree looks like. Oh, it implements display. Well, wait, why does the function... I have many questions. Let's look at parse first. Why? Oh, because parse consumes. Okay, great. Did that just work? It's a long way to get to a nest expression. It's true. But like... That's kind of cool. I mean, okay. If we do something more exciting, we do a.foo call with true 42 hello banana plus also didn't like that. Bad token and parse. That error is not good enough. 561. So this is an infix. Where's the place where we did this better last time? Here. So this is when we expect an infix operator in expression. Do I get a better error now? Here, unexpected token, right paren. So this means we're forgetting to eat a right paren somewhere. So we're forgetting to eat in parse statement within here. When we hit a left paren, we never even get there. I think something's wrong with the depth here. You need to stop parsing expression when seeing an end paren. I think you're right. So what you're saying is something like here, if I see a right paren, then that actually means no, it's not at the start of an expression. It is here. Let's think about what happens here. So we see the opening paren. And so we decide to parse this as a group. So that means we call parse expression next. The parse expression sees an ident as the left-hand side. It sees a dot as the next. And then it knows the dot is an infix operator. So it should hit down here. And so at that point, it should here say parse expression within with the binding power of dot. And it should return if it ever drops below the right-hand side of the infix binding power here. So I think what that means is yeah, I think it does try to parse the parens, but I'm trying to figure out why. Because I think it should terminate here, right? So okay, we're hitting field, so it returns 14 and 13. It returns 14 and 13. And so it checks whether 14 is less than 0, which is not. So it continues, which is correct. And then it passes in 13 as the right-hand side. And it tries to parse an expression there. Then it hits an ident as the left-hand side. And then it hits a close paren as the operator. So when it hits a close paren as the operator, that feels like it should stop. So let's go look at the Pratt parser here, the original one. It feels like there has to be a check here for end paren. And it's surprising to me that there isn't, because like how else does it know? Open bracket means you walk in with 0. Oh, but they don't have, they do have dot. Oh, but dot for them is different. Dot for them is function composition. Dot for them is function composition, which is supposed to be left associative. We basically need to try to figure out whether dot should prefer, whether it should bind more strongly to the right or to the left. But I think either way, it shouldn't make a difference, because I still don't see how this terminates. I still don't see how that terminates. Unless the end of file here becomes special somehow, but I don't think it is. I think it's just everything turns into an atom or an op, and end of file is just what you get instead of none. And I don't think this grammar is... Actually, maybe this is a part of the grammar that they just don't have, right? This notion of having two parenthesized groups next to each other. And I think that might actually require special handling. Although no, because a simpler version of this, right, is... in fact, we have comments, so we can get rid of that entirely. What if I just write 1 plus 2 in parentheses? Yeah, that hits the same error. On the right-hand side, expected an infix operator. So here's what I want to do now, which is I want to take this whole thing from Matclad. And I want to see that's no good. I'm actually just gonna do lib mod Matclad. And then I'm just gonna cargo T. And sure, I'll bring in the things that they need. Wait, what? Did I not bring all the tests with? I don't understand. There we go. What? Oh, great. Okay. So I want to see what happens if I put a top level expression right here. Well, that parses correctly, doesn't it? Looks like it terminates on break after not finding infix. Oh, did I might just have mistranslated here. It if lets sum. No, because this is where we end up panicking. Is the right parent being consumed instead of being peaked when trying to end parse inner? I don't think so, because I think what we run into is that we hit the infix case, right, with our right here. I mean, we can test it just in case, but I'm pretty sure we hit this with our field access. Okay, we'll take the simpler example, right? We hit this with a plus, and then when we go to parse the right-hand side, then we go back up, we find a literal number as the left-hand side, we enter the loop, we peek for the next operator, and the next thing we find is an end paren. And so it does feel here like we should sort of break here if we hit an end paren. What surprises me is that Matclad's parser does not have to do the same thing. And why? Why does their inner parser not hit this problem? End paren is an operator for them. Is that true? For them, it is a valid, end paren is a valid operator. I see. So they don't hit the panic. They just hit the fact that it's neither type of operator. Oh. And so that is equivalent to saying that a right paren is a break, right? Because if we made it an op, then we would match here on an op, and then we'd pass that op to this and get none, and to this and get none, and so hit the break. So those end up being equivalent. Great. So now back to our original thing. Okay. In argument list of function call, look at this error message. Missing open parenthesis. That is because in the function call that we parse out here, or where do we do that? Statement expression as a function call, so that's up here. So we're parsing the call, which means we're in the postfix case of call. So it should be the case that we're in here. Let's just check that that is actually the case. Foo. Great. Foo. I see foo. Okay, so we are in this case, and then we decide to parse the function call arguments. And so the next here, oh, the next here eats the open paren is why. Because it has to eat the operator. I see. It has to eat the operator. So that we don't start parsing the operator. Okay, so I think that means the parse function call arguments should not eat the left paren. So this is do not parent has already eaten left paren as the operator. Expected an infix operator. So this is because, again, comma isn't recognized as an operator. And so when we hit in the expression context down here, where is that? Here. So if we hit right paren or comma, or, and just because I know it'll end up happening, or semicolon, or any else? I think it's those. Those all mean that we should break because we've hit something that must be the end of an expression. Or rather, something that can't be an infix operator. It's not something that can't be in an expression, it's just it can't be an infix operator. Dot A of foo is the thing to call as the first argument, followed by true, followed by 42, plus a followed by a plus of hello banana and also. Easy way is just break on any non-operator token. Yeah, the problem is we don't have a distinction of what is a non-operator token. But how about that though? Do we have something fancier? Like if that, and if requires brackets, and new lines are allowed, and we'll add some indentation, then print, what else can we do that's complicated? Print A plus B times C divided by D. Else, if foo, like an ident, foo plus 42. Foo plus divided by 2. And not an else in this if. And return false. Let's see. Here, in body of if, okay, so notice it's in an if, missing end of curly bracket. Oh, this is, I think, because of our semicolon in here. No. In body of if, missing end curly bracket. So this suggests that print is parsing wrong. Print is only eating one thing. Why is print only eating one thing? Where's our prefix? Print and return should both do this. I think this is where we have to be a little bit careful with the binding. Yeah, I think the binding power is wrong. Because parse expression within is correct here, but I think we need to be careful with the minus. Or maybe it's not even the minus, but I think it needs to bind. I think return actually needs to bind really weakly. Like bang and minus both bind very strongly, but return and print need to basically not bind at all. So I think we want those to be 1. And then bang, we want to be something that's very high, but not higher than postfix, which should bind even more tightly. So that got further. In body of if, in the right-hand side, okay, this, we need a little bit more context here to really understand what's going on there. On the right-hand side of op, on the right-hand side of print, I want more context for my error. On the right-hand side of and I guess we can actually, here we can print the left-hand side and the operator, right? And I think that they implement display now too. On the right-hand side of print, print, null, print. Okay, that's less helpful. This one should just say that. On the right-hand side of print, on the right-hand side of A+, on the right-hand side of multiplication of B and C divided by, expected an infix operator at D. Oh, that's because I thought I was smart enough, but I was not. This needs to include token kind right brace as well. Haha. Okay, if where this is the condition, then print that which looks correct to me, and if that, then the print ends where? The print ends, this goes to that, this goes to that, this goes to that. Oh, so this is the else, and in the else there is an if. And this pluses foo to that division. That is the condition for the if. That is the yes branch for the if, and there is no else branch. I think, therefore I am. That's pretty good. Okay, here's what I'm gonna do. I don't think there's any point in pushing this. And the reason why is because I suspect that we will have to... Oh! So we happen to actually produce output that's not entirely wrong. What's the intended output here? What's group supposed to be? Interesting. So we don't even have groups anymore. So the fact that it requires me to print group is a little awkward because I don't have the groups. The groups are implied by the parsing. Yeah, group is a parenthesized expression, but we throw those away. But we can add those pretty easily back. Right? Because where we parse parenthesized expressions, which is down in here, we can just have this produce, instead of a left-hand side, we can have it produce a token tree cons op group. I mean, it's entirely unnecessary, but right? Cons, and then I just need op group. So we're gonna add a group here, and we're gonna add a group here. Sure. And so now if I run this again, I don't have any groups. Give me a group. Print this group. Oh, it's still not a group. Parse expression within. Oh, right. It's because I need to do that here as well. Token tree cons op group vec this. How about now? Okay, now we have a group. The numbers should be printed as with our fancy output thing, which we had earlier. So that's in Lex. We have this thing, right? Number. So this needs this, sadly. Okay. So that now prints those. And so let's see if for this expression, p sub. Ooh. Crashes. Why does it crash? Oh boy. Expected an operator. Unexpected token. What? Oh, right. Some token. Expected an operator there. What about without the negative number? So it's not the negative number. So here, it must be because we're... Well, this should produce a... Oh, it's because... I think it's because we parse it as a statement. And we don't consider... We don't consider expressions valid statements. Because my guess is this parse here is only supposed to be expressions. This is just for the expression parsing chapter. So all of this is just expressions until we get there. So is there a different... I'm just exploring. Run is going to be different. Okay. So that means parse is actually here parse expression within. So what we'll do is parse expression and then parse. This is just going to parse expressions within. This is going to do parse statement within, parse expression within. And so in main. So in parse, that's going to be different from in run. Run is going to do this and actually parse. This is just going to parse expression. No, parse expression. And run we haven't defined yet, but it's just going to be this. So now we can do for hours here, run. That does the right thing. The parse expects an expression. And so now this does the right thing. Now, does that match the output that is expected though? If we go over here, so if I do echo, those are exactly identical. Okay. Git add source lex, git add source parse, commit all of parsing, question mark. What else do we have? Okay, git push. See what happens. What? Fetch first? I don't understand. Why is there something? No, someone else is committing to my thing. someone else is committing to my thing. Git push Force with least. No, just force. I'm assuming it's someone from the website who's testing things. Well, something succeeded. This passed. Number literals. Test passed. String literals. That's running for an awfully long time. Test failed. Baz foo. Expected line to be Baz foo. I suppose I'm not supposed to print out the suppose I'm just I should just print strings straight out? That feels wrong. I think that's wrong. Right? Like if I write now foo here, then now it's the literal foo. I feel like that should print what I had, which was this. Surely the no expressions evaluate. No, that's evaluation. Surely the expectation is not that the print of a string is the content of the string without any quoting. That I think that's wrong, but okay. I will do this and say note. This feels more correct. But okay. Bad. We were on such a good run. I was hoping we'd just keep going through all of them. Okay, back to this. How about now? Okay, test passed. String literals, right? Test passed, yes. Mark stage is complete. Celebration, parentheses. Test pass, complete. Unary operators. Unary operators. Unary operators. Test pass. Arithmetic operators. See, this is why it's exciting to build the whole thing, is because then you can just go, yeah, I did the thing. Arithmetic operators 1 out of 2. Complete. I'm very glad we settled on the same output format that ended up being used. Arithmetic operators 2 out of 2. Yeah. Comparison operators. Test failed. Test failed. Whoa. 98 is greater than 84. That's just, here we're just doing wrong. 98 is greater than 84. Well, okay, that's just wrong, program. What are you doing? Hey, program, get your shit together. What? Oh, I know why this is. I know why this is. It's because we haven't defined those as being infix operators. Less equal, greater equal 3, 4. I don't really know what associativity they should have. Doesn't feel like it matters. But fine. Okay, while we're at it, are there other operators I missed? Minus, plus, star. Oh, bang, equal, and equal, equal. Bang, equal, equal, equal. What else? Oh, slash. Do we have slash? We might already have slash. We already have slash. Okay, great. And an or. I think and an or is the last one. So and an or. And an or. So and an or actually need to bind. I think we want them to bind very little. But they need to bind more than print and return. So they're going to be, it's going to be 3 and 4, which means this needs to be 4 and 5, which means this needs to be, wait, no, this needs to be 5 and 6. This needs to be 7 and 8. This needs to be 9 and 10. And then this is 11. This is the annoying part with the Pratt parser, as far as I've understood. This needs to be 11. This needs to be 12. I don't think it matters for call because it has a grouping operator around it. And then this has to be 13, 14. Or I think a good convention is they all start at odd, which would mean this starts at 5. This is 15, 16. More define BP for more ops. Push. Oh. Test passed. Great. I'm glad that these are trivial, right? Like the things where it doesn't work is like, oh, we just didn't define the operator precedence for them. Equality operators test passed. Syntactic errors. This is where we're going to fall short because we don't actually turn these into anything that's reasonable. Yeah, see, like we need to provide things like expect expression, which is easy, but not something I'm going to do now because it's way too late. I've already gone way longer than I was planning to. Okay, here's what we're going to do. It doesn't check the output format. Oh, it just checks the exit code. Oh, well, that's okay. If it's just checking the exit code, that's easy. So then we can just do... oh, it's actually a little bit annoying. But we can do... this is really stupid, but I'm going to do it anyway. Just to get it to do this. And so actually, I could even take this code. No, I wouldn't end up doing that. That's fine. And in fact, no, I don't want to do that. Instead, what I'll do... So I'm going to claim that certainly for parsing, it doesn't make sense to keep going. So here, we're going to say if we're going to match on this, and if we OK a token tree, then we're going to print line the token tree. If we get an error, then we're going to print line the entire error, and then we're going to exit with this. There is technically a way where you can have like a wrapped error type that lets you set the exit code. Oh, and I don't want to remove that quite yet. I guess actually I can hoist that up to here so that it is specific to tokenize. That is going to keep going. So just in here, I'm going to have that happen. Exit 65. Expected exit code 60. Oh, we, it's, okay. To do match line format, match error line format. But also we're actually panicking at parser 502, which is another one of those token ones where we can just copy paste the thing we already have to here. And this is supposed to be left-hand side of an expression. Expected an expression. Can I make this not mess with the... Nope. Okay, great. So that means the diff is ugly. More nice error. Git push. Boom. Test pass. Mark stage is complete. Okay. The next stage now is evaluation. Now, we're not going to do evaluation this time. I am very happy where we got to. We got to all of lexing and all of parsing. And now we have evaluation. We have statements. We haven't done too much with statements, but we have evaluation now. This was fun. I really liked this. I got to go through parsers. I got to debug a bunch. I got nice errors. I'm very happy. We're going to stop it there. I think I'm probably going to do a part 2 about this. This ended up very long, but it was because it was fun. So we kept going. What I will do is, and of course, if you're watching this after the fact, you already know that this is the case. I will upload this video on YouTube. I'll put a bunch of chapter marks for going through the different parts here. It'll be a little hard to break up the, I'll at least break up the lexer and parser. Subdivisions are probably going to be harder. Given how long this might come up for a little while, maybe like tomorrow evening or Monday or something. But this is fun. I'll remind you all that you can also do this challenge yourself. I'll put the link again in the chat here if you haven't found it already. And again, it'll be in the video description. Although if you're at this point, you've probably already realized that. So you can go in and try this yourself. It's in beta at the moment, as far as I can tell. So it's, yeah, as it says at the top, it's free during the beta. After the beta, it's no longer free. If you sign up through the link that I put in there, then I do get a referral, which is exciting. If you enjoy this, I think this is actually a useful learning sort of resource. That's why I do these streams. What I will say is that if you cannot, like, if you don't have the means to pay for something like this, it's not super cheap. Then these things are also available on GitHub, on the Codecrafters GitHub. They have all the sort of source content available. You just don't have any of the nice infrastructure and tooling and stuff that is here, but you can still learn through the resource. Or of course, the book itself, the Crafting Interpreters book, is also available, and it's just craftinginterpreters.com. And so far, I'm enjoying that a lot. So very excited. I'm going to end things there. Thanks for sticking with me if you're watching this on demand. And if you're here on stream, I have no idea how you stuck with me this long, but at least that suggests that this was interesting. That's all for me for today. And I will see you again in part 2, whenever that might happen. And if you're watching this as a recorded video, it might already have happened and it should be up here in the corner or something. It'll show up in an easy to find place. Thank you and see you next time. Whew. And of course, to the people who are watching me live on stream, thank you so much. It would not be the same without you all. This was a lot of fun, and it is way more fun to do it with you all because you have such great insights. Like, there were a bunch of places where I'm sure I would have been stuck for much longer if you didn't call me out on, you just mistyped this thing or forgot to reset Peekable and Next, for example. Thank you all. I'm going to go sleep now, but thanks for staying with me. See y'all.